So Tony, in the lab of today, you are going to show how to use this remote command, right?
I beg your pardon, Ivan, can you repeat?
I was asking in the lab of today, you are going to show how it works, this remote command.
Yes, I will try to do it now at the end of the presentation, if I will have time, yeah. Otherwise, also Ari will probably show how to do that.
Ari, okay. No, because I was saying it's better if we do it today because tomorrow I'm not here. So
no, because today, definitely today, because today the exercises start to be heavier, and they will be some of them. They will be definitely run on the HPC cluster.
Okay, I see. Okay, perfect. Sorry, the noise. It was me. Okay, I think we can start.
Can we start?
Yes.
Okay, good morning, good afternoon, good evening to everyone. Welcome to the third day of the MaX School on Advanced Materials Modeling with Quantum ESPRESSO. So I'm Alessandro Stroppa, and today I will be chairing this first session. So today there will be a lecture on forces, stresses, and geometry optimization, chasing saddle points, the nudge, elastic, and band method. And just a few preliminary remarks. After the talk, there will be a question session, and in this case, you can raise your hand, and you can have the word to ask directly the questions. For those who are attending on Zoom, we kindly ask to write their questions on the Slack channel in the day 3 thread. And so I'll leave the speaker of today are Pietro De Lugas from SISA, Italy, and Anton Kokal from Josef Stefan Institute, Slovenia. So please.
Alessandro, just before Pietro starts, maybe just if we agree with Pietro, so how we do this question session, because first Pietro will present a talk, and then I will present a talk. And so maybe I suggest that when Pietro finishes, then there is a session question for his talk, and then I can start, and then after.
Okay, so after Pietro part, we will have a question session. Okay.
Well, yeah. Okay. Yeah. We have to be okay.
Thank you. Please.
Okay. So this is my. Let me share my presentation. Then I go to full screen mode. Now, can you see the presentation now?
Yes, please.
Yes. Okay. So, good morning, everybody, and greetings to everybody. And I will give the first part of this lecture, and I will talk to you about force calculation, stress calculation, and how we can use this information to perform structural optimization. And I also added a few slides about doing molecular dynamics with PW.X in the Born-Oppenheimer molecular dynamics. This is the outline of this part of the lecture. First, I will introduce briefly what are the structural parameters that I'm talking about. Then I will talk how forces are computed in Quantum ESPRESSO, more than how the forces are computed, what is the theory behind the computation of the forces, and the implication that this theory has, and the caveats that one has to keep in mind when it's using this information to perform structural optimization. Then I will also speak about the stress computation, and then I will present the optimization methods that are present in the Quantum ESPRESSO, in PW.X and in Quantum ESPRESSO, and I forgot to add here in the outline, but there will be also a few slides about Born-Oppenheimer molecular dynamics. So, structural parameters. What are the structural parameters? When we define a system to be computed in PW in Quantum ESPRESSO, we specify the number of the atoms, the number of the atoms and the species. And in particular, when we specify the species, we specify the pseudo potential that is used to simulate that kind of ion. And then we specify the position of the ions. We specify the spatial relation between the ions, and we call it, and I'm calling it here, this the structure of our system. The structure of this, we are in Quantum ESPRESSO, as we have already heard in the first two lectures, we are using periodic boundary conditions. So the structure of, we are dealing with a periodic infinite system. And so to specify the structure, we need two things. We need the position, the atomic, we need to specify the atomic positions, but we need also to specify the lattice parameters. We need to specify how the periodicity of the cell is, and how these atoms are repeated periodically in infinite times periodically in the space. Obviously, obviously, it's not possible to change the lattice parameter without also changing the lattice position, because these two quantities actually interact. To keep them well distinguished, we usually use the fractional or the so-called fractional or crystal coordinates. In this case, the position of the ionic position of the atoms is expressed in terms of the components of the lattice parameters. These xi numbers that I'm indicating here are numbers that are included between 0 and 1, so they specify the position of the atom in the unit cell, and they are periodically repeated all over the spaces I was saying. All these structural parameters, so the position of the ions and the lattice parameter, provide what we call a potential energy surface where our system may move, and the purpose of the structural optimization is to look for minima in this potential energy surface, or to understand how the atoms may move in this potential energy surface. So the first to be able to do this, we need to compute the derivative of this potential energy surface with respect to the parameters. The first derivatives are the forces, that are the derivatives of the energy with respect to the of the total energy with respect to the atomic positions. And we can divide it in two parts. One first part, that is the other forces that are given by the derivative of the electronic part of the energy. And the second part is instead given by the derivative of the electrostatic interaction between the ions. While the second part, this part is trivially dependent only on the position of the atoms. For the first part, to express it as only function of the position of the atom and of the ground state density, we need to use the Hellman-Feynman theorem that applies in the FT as it applies in standard quantum mechanics. And thanks to this theorem and thanks to this fact, we know that we can compute the derivative of the electronic part of the energy, of the total energy, as just as the expectation value of the derivative of the potential with respect to the ionic position. And for local potential also with this integral, this is just the integral of the derivative of the electronic potential with respect to the density. So we are using the Hellman-Feynman theorem, and as long as the demonstration is easy, I will not give here a thorough demonstration, but just to say on what fact this is based. This is based on the fact that we are that the energy is variational with respect to the density, so with respect to the variation of the density. That means that at convergence, so at when you are at the minimum of the energy, the functional derivative of the total energy with respect to the charge density integrated times any variation of the charge density that integrates to zero, because we are conserving the total density of the system, also integrates to zero. This requirement means that the functional derivative of the total energy with respect to the with respect to the charge density is a constant and doesn't change in space. So when we compute the derivative of the total energy with respect to the atomic position, we have in principle two terms. One term is the one that we are using, is the one that is present in the Hellman-Feynman forces, plus a second term that instead is of this type, is the possible contribution to the forces that is given by the variation of the charge density when we move the ions. This term integrates to zero because we have this condition. So the charge, the functional derivative of the total energy with respect to the electronic density is a constant. Okay, this fact allows us to compute the forces with just as an expectation value, but the problem is that this fact is true only if we are at full convergence, and this fact is exact. So our forces are accurate only when we are very close to convergence. Otherwise, obviously, we have an error on the forces, we have an inaccuracy on the evaluation of the forces, and the program pw.x actually prints an estimate on the value of this red term, on this possible inaccuracy in the evaluation of the forces. And it does it with an approximate correction that it was proposed by Chan and others in a paper of 1993. And for doing this, we have an estimate on the derivative of the charge density with respect to the ionic position, and this one is estimated using a superposition of atomic charge densities and computing the derivative of this one with respect to the atomic position, while instead the functional derivative of the total energy with respect to the charge density is estimated using the difference of the self-consistent potential in the latest two interaction in between the final interaction. In this way, we can compute this integral, and this integral gives us an estimate of the correction that we have to give to the forces. During relaxation of molecular dynamic simulations, the program, if you have a look at an output of the program, you will see that prints out this estimate, and if the inaccuracy that the program has estimated is comparable in magnitude with the forces that are actually calculated, it raises a warning. This problem may actually arise many times when we are performing structural optimization, because obviously when you are performing structural optimization, you arrive at a point where the forces are very small, and so you need more precision of the forces. The program usually progressively lowers the threshold for the self-consistent convergence. So it tries to avoid this problem, but it's always good to look at this evaluation and see if any issue is raising there, because especially when the forces are very small, there is always the possibility to to have an inaccurate evaluation of the forces, and so all the dynamics, all the structural optimization fails. Okay, and the second the second structural so the second derivative that we are going to compute is the one of the lattice vectors. To characterize the change of the lattice vectors, we use the strain tensor. The strain tensor is being divided to describe the uniform deformation of in principle, infinite system. It is a linear function. You just take any point in the space, and its coordinate passes from r to r prime according to this linear relation. And so any change in the lattice vector may be described by this quantity E alpha beta. And so the derivatives and as forces, we use the stress tensor that is computed as the derivative of the energy per unit volume with respect to the strain. So it's -1 over omega, where omega is the volume of the unit cell, derivative of the total energy per unit cell with respect to the strain. And it is to note that as it is written here, there is no constraint on the fact that E alpha beta must be symmetric or antisymmetric or whatever, maybe anything. But it is a fact that only the symmetric part of this tensor affects the total energy, because while the symmetric part is actually a strain, the antisymmetric part of this tensor comes out that is only a solid rotation of the system that doesn't change the total energy of the system. So if you by any chance were going to have to do an evaluation of the stress by finite differences, you should be aware that your strain must be symmetric, or you have to symmetrize it before computing this derivative. So the stress tensor has in total 9 components. So it's given by 9 components. It forms a matrix, and so the diagonal terms of the stress tensor are related to the pressure, and are those that are directed perpendicular to the face. So these are the forces per unit surface that the system that each unit cell exerts on the neighboring unit cells. Together with the diagonal terms that are related to the pressure, we have also the shear components of the stress that are the off-diagonal ones that express the tendency of the system to have deformation that are parallel to the surface of the unit cell, and tend to deform the angle between the lattice, the angles between the lattice vectors. Also, for the stress, there is also the stress is a first derivative with respect to an external parameter. So we can also here use the Hellman-Feynman theorem. It is a little bit more complicated to compute, and it was computed by Martin in the 80s, and in this case it doesn't depend explicitly on the ionic position, but just depends on the but it must be computed as a derivative of the kinetic energy operator, the Artin and exchange correlation potential with respect to a uniform deformation of the space. So it just involves the components of the plane waves. As I was saying, it involves the components of the plane waves. So it means that the strain actually depends on the depends on the basis set that you are using, and at variance with the forces that we have. Okay, I forgot to mention, in plane waves, the forces have no Pulley component, so the forces do not depend on the basis set. This is a pro of the plane waves. This is not true for the stress. Instead, indeed, the stress instead depends on the basis set that you are using. This was a thing that Ralph Gebauer also mentioned in the first lecture. If you change the lattice parameters, for example, here, and you decrease or increase the value of the lattice constant A, you see that the density of wave vectors inside the sphere of the cutoff changes. So you are changing the number of wave vectors inside your basis set, and when you deform the cell, you are also actually changing the length of this, the length and the metric of this basis set, and this affects the total energy and it affects the stress. This gives, for this reason, the evaluation of the energy and of the stress can be discontinuous when you are using a cutoff that is not at full convergence. So full convergence means that your cutoff is so large that all the plane waves that are close to the border gives a vanishing contribution to the total energy, to the stress, and so on and so forth. These discontinuities may force you to use a very large cutoff to compute stress and to perform when you perform variable cell relaxation. And there is actually another technique that allows you to avoid this problem or to regularize this problem, and this is the so-called smooth cutoff. When you use the smooth cutoff, what you do is actually to redefine the kinetic energy functional. Usually, the kinetic energy functional is just g square. So you just compute for each plane wave, you just compute the square of the square of the modulus of the vector, and that one is the kinetic energy of that plane wave. And but if you rewrite the kinetic energy operator in this way, you are adding another term. This term is okay. Here we add this term. This term is done by 1 plus the error function of g square minus a cutoff value and the sigma width. It happens that this when g square is much smaller, is less than EC fix and is far, and they are one far apart of the distance that is much larger than sigma. It happens that this function here is evaluates to -1. So this term vanishes and your kinetic energy is the same as in the standard kinetic energy functional. While you are approaching, when g square approaches the cutoff, instead you see that this value starts raising from -1 to 0 and then to 1, and so you are adding an additive penalty term to the kinetic energy, and so your plane wave in this region here, so your plane wave in this region here starts having an energy cost, and so when you perform the minimization of the Hamiltonian, what happens is that these plane waves are the weight of these plane waves on the ground state wave functions becomes smaller and smaller, and so their weight it changes regularly from some sizable value to a penalized value without having an abrupt cutoff with wave vectors that enter and that come in and out from the evaluation of the kinetic energy operator. In pw.x, this is implemented with these three variables. So you specify EC field, that is the value of this yellow, of this orange cutoff here. So you select an additional cutoff that has obviously to be a little bit smaller than the cutoff that you specify with ECAT WFC, in order that you have a region whose width is defined by QE sigma, where the plane waves that are in this region have a smooth entering or going out from being significant for your system, and then you have also to specify the height, the height, this value here, and it is how much you want to penalize the function, the plane waves that are in this region. In this way, you regularize. You have a more regular evaluation of the stress, and you have and you can perform also a variable cell simulation without being at full convergence with the cut WFC cutoff. So now we pass to the so now that we have seen how we can compute forces and stresses, we pass to see how in pw.x it's possible to use these derivatives to perform structural optimization. You can perform two kinds of structural optimization. One is structural optimization on fixed cells. So you leave the lattice vectors unchanged and to their value, and you just relax the atomic position using as the gradients and derivatives the forces of the atoms. The second type of structural optimization that you can perform is instead one where you optimize both the atomic position and the atomic position and the lattice vectors as coordinates as a coordinate for the lattice vectors. We will use the cell strains, and in this case the gradients are given by the forces of the atoms, as obviously, and by the stress tensor. You may use two different algorithms to perform the structural optimization in PW. The most important one, the most used one, the default one, is BFGS. So you have to specify in ion dynamics by BFGS. Actually, you don't need to specify it because it is the default value. So if you don't specify anything, the program will assume that you want to use BFGS. When you want to perform VC relax calculation, you have to specify BFGS and ion dynamics, or just leave it unspecified, and the program will select it. And you have also to specify in the cell in the cell name list the same variable for the cell vectors, cell dynamics equal BFGS. There is also another algorithm that is called the algorithm for the damped dynamics. In this case, you have to specify ion dynamics equal damp in the ion name list. While instead, for the cell dynamics, you have to choose between damp PR, that means damp Parinello-Raman, or damp W for the Venskovich damped dynamics. You have to specify these ones because when you perform variable cell, you have to specify these ones because when you do this algorithm, what you are actually doing is to perform a molecular dynamics simulation that is damped. So damped means that you progressively drain the kinetic energy out of the system. So the system, the forces of the system accelerate the system, so increase the kinetic energy of the system to as it falls to the minimum. And in order that the system remains close to the minimum, you just in some way remove the kinetic energy of the system. In quick mean, this is done in a very simple way. You just monitor the velocity of each of the components, and and as long as the forces and the velocities are parallel, you just keep the system falling down. But as soon as you see that the forces and the velocities have opposite direction, that means that in that direction, the system has passed to the minimum. So now is going uphill. You just remove the kinetic energy of that degree of freedom. In this way, the system forgets about the energy that accumulated before and starts running down, starts going downhill again in that direction. The pros of this algorithm is very robust because it's very simple, so it just doesn't make any assumption on the system, on the position of the minimum or anything like that. And even if the starting point is not close to the minimum, it goes, it works. It has also some non-good qualities. So to use it, especially when you do variable cell, when you do it in variable cell, you need some experience because you need to be able to understand if you want to use the damp Parinello-Raman dynamics or the damp Wenzkovich dynamics to do the simulation. And the other thing is that you need to be able to choose the time step for the dynamic, and you have also to be able to understand what is the best value for the fictitious mass of the cell. And the other thing that obviously is not good of that is that in most of the cases, if you do the same optimization with BFGS, you usually do it, you usually finish, I mean, it's generally slower than BFGS. So if one usually tries damper dynamics only when it finds that BFGS fails. So now I come to present very briefly how BFGS works. Okay, the BFGS stays for the name of the four mathematicians that have published this method: Broyden, Fletcher, Goldfarb, and Shano. And this is the algorithm that is used by default, as I was saying, and is it generally works very, very fine, and it belongs to the family of quasi-Newton algorithms. And it starts by an assumption that you are close to the minimum. So meaning that close to the minimum means that your energy as function of the position may be expressed as the value at the minimum plus a quadratic term on the displacement. So you have that it's expressed by so you have to okay, here you have to make an hypothesis on how this quadratic form is done. So you have to create an hypothesis of the axial matrix as the second derivative of the total energy, and along your minimization you have to update this guess of your axial matrix. And actually the BFGS stays for the algorithm for updating this axial matrix. The algorithm works in this way: you just compute the forces, so it's just the gradient of the energy, and then you just compute the updated position using the Newton-Raphson step. So you just say that your gradient at step 1 minus your gradient at step, the gradient you are looking for the step 1 for which the gradient minus the gradient at step 0 is given by the Hessian times the position at step 0 and the position at step 1 that you are looking for minus the position at step 0. And imposing that the gradient at step 1 is 0, you find that your search direction is given by x0 minus the inverse of the Hessian that multiplies for the gradient at step 0. This means that suppose that you have a good guess for the Hessian, you are able, just knowing the position and the force at step 0, to have a good guess of the position at step 1. In practice, you don't do this. You just use this information here. This information here, that is this one, as a guess of the direction in which to look for the minimum, and you set the new position as the old position plus thrust radius times the direction where you want to go. So as in the following steps, then you have to update your inverse Hessian matrix. The update is quite complex to tell. Is made by many. It's proposed in this formula, and is a function of the on the search. Okay, by default is like this. So by default it is a function of the search direction at your point plus the change in the lattice vectors plus the change in the gradients in the two lattice steps, and you have an update of this kind. This is actually the BFGS scheme for the updating it, and there are also other schemes. Also in Quantum ESPRESSO, you may select, there is a variable that is called BFGS and dim, where instead of using only the latest step, you can use also more steps from the search. But obviously this assumes that you are actually in close to a minimum, because the more steps you are using, the more you rely on the fact that you are close to a quadratic minimum. The other thing that you have to do is to evaluate this thrust radius. To evaluate the thrust radius at each step, you just do two checks that you have that your thrust radius satisfies the two Wolff conditions. The first Wolff condition is that the new energy must be lower than the old one plus W1 times the thrust radius that you are currently using times the gradient times the search direction. W1 is a variable that you can set in the input of pw.x, and it has a default of 0.001, so it's very small, and this condition is usually verified anytime that your new energy is lower than your old energy. Then in order to satisfy a second condition, there is the curvature condition that instead tells you that this condition checks that you are not going too far. So if you have this if this condition fails, it means that this step it was too long, and you went too much over the minimum, and you missed it, and you are on the other side of the minimum, and you are getting wrong for that. The second condition instead checks that you are not being too close to the previous minimum, and checks that your slope is decreased enough. So it means that this is an estimate of the slope in the new step. This one must be larger than W2 times the estimate of the slope in the previous step. In this way, you are checking that your step is not too short, and in case the trust radius is increased in order to have faster convergence. This is the algorithm. It generally works fine, and it has anyhow some problems in some cases. So the first problem is that the first problem of this algorithm is that usually, but also quick mean, usually converges to the closest minimum. So the minimum you have an initial position, you have a Bayesian of accretion of this position, and the structural optimization will fall down to this closest minimum. That it may not be the local minimum, the global minimum that you are looking for, because if there is any potential barrier that prevents you from going to that minimum, you will not go there. But I think that Tone will show you other methods to find global minimum, or to find how to overcome potential barriers. And then the other thing is that the structural optimization is anyhow constrained to stay at the same crystal symmetry that you have as the starting point. So this is sometimes a good thing, because you are actually looking for a minimum that has the same symmetry that you have imposed to the system for starting, but the global minimum may actually break this crystal symmetry, and your structural optimization will not be able to find it. Actually, there is also the opposite problem, because sometimes you are actually looking for a minimum within the constraint of the symmetry that you have imposed to the system, but due to numerical noise, sometimes the symmetry is broken, and the structural optimization gets a little bit lost and starts deforming, for example, your lattice vectors, and you may lose. Your structural optimization in this case may fail, because you are for numerical noise breaking the symmetry. The other problem is for when you perform variable cell optimization. The algorithm is done assuming that your starting lattice vectors are not too far from those that you will get at the end of the optimization. So for reasons of efficiency and regularity of the evaluation of forces and stress, usually the basis set is kept fixed. So it's not you start the simulation, the program checks the cutoff, checks what are the Miller indices of the basis set that are within the cutoff, and those are the basis sets that you will use for all along the structural optimization, the variable cell structural optimization. What may happen is that if your lattice vector change significantly, what happens is that this basis set may be significantly different from what from the starting one. So as a final check, as a final check, the program at the end of a variable cell structural optimization, after it has obtained the final lattice vectors, the program performs a final check. So it just takes the final vectors, recomputes the plane wave basis set, and recomputes the total energy in this case. So in many cases, you will find that the energy in the evolution of the energy in the relaxation is the downhill. So you have that the value of the total energy reduces until you get at convergence. But then you will find that the very last calculation, so the very last total energy instead as an ion energy. This is due to the fact that this last calculation is being performed with the updated basis set. So look at the energy difference between those two, and if they are significantly different, it is maybe worth to perform a further check to see if that one is actually the minimum that you were looking for. So the other important thing to remember is again the fact that when you minimize, when you are performing a structural optimization, the forces become smaller and smaller and smaller, and so when you are very close to the minimum, the fact that the so-called self-consistent error that I show you at the beginning of the talk may become significant and may hinder the convergence in the very last steps of the structural optimization. So okay, now we have seen how to use the forces and the calculation of the stress to perform structural optimization, and we just dedicated a few last slides to see how instead we can also use the forces to perform a molecular dynamic simulation in Born-Oppenheimer molecular dynamics with PW. So the principles are the same as the classical molecular dynamics. You have a kinetic energy that is given by the usual term minus the potential energy that is defined by the values of the lattice of the atomic position, plus if you are doing variable cell molecular dynamics, also the parameters of the cell. You write with these two terms a Lagrangian. You apply the you apply the usual Euler-Lagrange equations, and you find your equation of motion that are actually the usual equation of motion that with the usual equation of motion. So they just that can be this that you can use to use to perform molecular dynamic simulation. To actually perform molecular dynamic simulation, you have obviously to discretize it. So you have to pass from continuous time to the discrete time step. In PW, there are available two Verlet algorithms. The first one is the standard Verlet algorithms, where you have standard Verlet algorithms, but you can also use the velocity Verlet algorithms that that both of these two methods allow you to compute to do molecular dynamic simulation in the microcanonical ensemble. So it means that at constant energy, and so that you can perform with these two simulation at constant energy, where the total kinetic energy plus the potential energy is in principle conserved. Obviously, the conservation of the total energy depends on the accuracy of forces. And one thing that is important to set up is to have to use a small time step. The time step should be something that is it should be 100 to 1/10 of the period of the fastest phonon vibrational mode, in order that obviously no, you are obviously not going you are not obviously going too fast with the dynamics. And then the other point that I was mentioning is that you need forces that are accurate enough in order that the energy is conserved. Otherwise, you will find that your dynamics will have a systematic drift due to the fact that your forces are not you are not computing accurately enough the derivative of the energy, so you are accumulating error upon error, and in the end you have a drift of the conserved energy. For these reasons, performing molecular dynamics simulation with PW is much more expensive than what you can, for example, we'll see in the lecture of day 8, where you will see that it's a little bit more convenient to perform Carr-Parinello molecular dynamics instead of Born-Oppenheimer molecular dynamics. And this is all, and thanks for your attention.
Thank you very much, Pietro. I don't know, Alessandro, sorry, I wanted just to mention the people that are following in streaming. Unfortunately, today we made a mistake. We activated the chat later. So if you want to make a question to the speaker, please reload your YouTube page, and you will find the same page with the chat loaded. Thank you, Pietro. Thank you for the nice talk.
Okay, so thank you, Pietro, for a very nice talk and so detailed. So the session is open for questions. For those who are attending on Zoom, they can raise their hand and we can unmute them. Do you have any questions? Okay, so let me read the question from Zlak's channel. So how can we sure that the optimized structure is a global minimum? Because in principle, we can be trapped in some local minimum.
That's true. The problem is that you need to. Okay, it depends on the system. Obviously, if you start from a position that is close to the minimum that you were looking for, probably you will end up there, and you may never be sure that that is the global minimum. If the system is simple, so simple and symmetric, you may assume that the the minimum should stay in a position that has some symmetry, so you can check the various symmetric points and starts from those ones and see if compare the various energy of those systems. For example, this is what people used to do with defects in silicon, in germanium, in semiconductors. In those cases, you started from a symmetric position, you minimized all these symmetric position, and then you compare the minima of all these local minimum and see what was the most favorite one. And then if the system is complex, actually, unless the local minimum is very deep, then if you have many minima, also the entropy is important, I think. So it's good to find the many minima. And for complex cases, I think that techniques like molecular, like metadynamics and other techniques for exploring the energy landscape are much more suited than structural optimization. Structural optimization is for systems where you have some good theoretical reason to assume that the minimum is in a few selected places. Otherwise, if you have to explore a complex energy landscape, it's much better to use more complex techniques than just simple structural optimization.
Okay, thanks. Thank you very much. So there is a question from Dorius. I think you can ask directly the question. Yes, please.
Good morning. Good morning again from Spain. Looking at this interesting discussion of how atomic forces are calculated, I was thinking in a material which is being strained. So experimental scientists often knows that at certain level of strain, the material is going to break. So I'm afraid if I'm studying, for example, some properties which become more interesting as I stretch, maybe the more I stretch, the more interesting are going to be my properties, but at a certain point, they are going to be unreal. So I saw the physics behind this is complex, so maybe this doesn't work in this way, but I think it should be really beautiful to see this effect of the extreme case when the material is broken in the evolution of the atomic forces under strain. But also, I noticed you point out that in the case atomic forces are really small, we have to be really careful. So it's possible to capture this scenario in which our results are going to become unreal.
Okay, as for breaking of the material, there is a lot of work on fractal dynamics that is actually, it was a very active field where actually the breaking of the material usually happens at a scale that is a little bit much larger than systems that usually are. So you need to set up a machinery that is able to work on a multi-scale scenario usually, because breaking of the material happens to larger scale. So you have to combine ab-initio forces, the computation of the ab-initio computational forces and energy with other methods, like there was a lot of work done with machine learning techniques, with learn on the fly techniques, so that you perform a simulation, you learn a simulation where you train the forces by ab-initio, and you for a certain time until the forces are fine, you continue with your empirical forces computed by the ab-initio ones, and I think there is a lot of work on that. It's more, this is a thing that requires a multi-scale approach, where you cannot only use just ab-initio, because ab-initio, even if done at exascale machines, even if done with 10,000 atoms, even if done with 100,000 atoms, maybe for some cases where the material breaks are still not enough, and are cases where the thermodynamics, the disorder plays a role. And so I think that in those cases, it's combining the methods, it's much better.
Okay, thank you.
Thank you.
Thank you, Pietro. So some other questions. There is a technical issue, how to calculate the cell parameters ABC when declaring Ab equal to 0 in the input file.
So I didn't get the question.
How
so you set Ab equals 0, so you also specify in input the three lattices. Then that means that you already know them, and then yes, okay.
To perform the relaxation. I mean, if you can vary the.
No, maybe I understood the question. So yes, so you have put there that you are using Ab equals 0. You have your lattice parameters put in input in the cell parameters card, and then the lattice obviously the relaxation prints out you the deformation in terms of the initial lattice parameters. It may be a little complicated, but I think that the program prints out the deformation of the lattice parameters. So you have just to use the formula that I set here, and it will be possible if you use just this formula with the deformation parameters, just to get the new ones. It's okay. It's not directly immediate, but not that complicated, even if I think it's much harder to tell you by voice than to do that. So, okay, sorry, I didn't actually answer, but.
Okay. So some more question. Is there any option to calculate the vibrational frequencies of the structure during geometry optimization?
Okay, if the Hessian vector, if the Hessian matrix was accurate, yes, but that means that you are actually close to a quadratic minimum, and you don't know that. Usually, when you use BFGS, you just set the dimension of the steps that you are conserving to 1. That means that you actually don't trust too much the hypothesis that you are close to a quadratic minimum. And in principle, yes. In practice, people doesn't do that. You just first find the minimum, and then either you compute the Hessian by the with the phonon code, or if if you wish, you can also compute that by finite difference. So once you are in the minimum, you just displace of the atoms and compute the derivatives.
Okay.
Process.
Thanks. Then in VC Relax, how to choose which option for cell do free?
Okay, that depends on what you are looking for. If usually people, okay, for example, if you just want to optimize the iBrav parameters, so CLDM1, CLDM2, 3, 4, 5, and C, all the lattice parameter, and you have specified your vector with iBrav, I would go with the iBrav option that just keeps you in the Brav that you have selected at the beginning and avoids any problem with symmetry and goes straight to there. If instead you don't know where you want to go and you want to set, you can put it, you can just set you can just leave the default and this Relax will find for the minimum by itself. Obviously, as I was saying in the talk, if there are symmetries that in the starting configuration, these symmetries should be conserved. If they're not conserved, it's because of numerical noise. So it's not even sure that it's safe. But okay. But in any case, it depends on what you're looking for. So all those options are for example, if you have a system where if you have a two-dimensional system and you want just to optimize the lattice constant in plane, the in-plane lattice constant and not the normal one, you have to use the potential options. Otherwise, if you want to constrain the lattice constant in plane, you just optimize the orthonormal one. You have to do the opposite, and there are many of them. They are explained hopefully well in the input PW guide, and it's okay. Just that.
So I think we can get another question, but probably we have to give the word to Tone. So last question. So can we use some umbrella sampling technique to sample the energy landscape in molecular dynamics?
They are used. I mean, there's a lot of people that is working in. I mean, there used to be a Plummed interface for performing such tasks. Now there is a very good interface with IPy that I don't know if performs this kind of stuff, but yes, you usually need to rely on external codes that then use Quantum ESPRESSO just as a quantum engine, a force engine, so they just compute the forces and use them. Yes, there are a lot of possible ways to do that, but not just simply using Quantum ESPRESSO, but using Quantum ESPRESSO together with other tools.
some multi-software approach.
Yeah.
Okay, so I think we can stop here because there is another part from Ton. We thank you very much, Pietro, for this night talk and these explanations. So the session is now ready for Anton that will continue some, I think, nudge elastic band method. Please.
Thank you very much, Alessandro. Now let me first try to share the screen. Okay, let's see. So can you see my screen?
Yes.
Yes, okay. So hello everybody. My name is Anton Kokal, known as Tone to colleagues and friends. And now I will present an Ab method, which is a method that can, let's say, calculate saddle points. And to make a bit of a context for this saddle point business, let me say that this will be about activated processes. And activated processes are processes that are characterized by energy barrier. And a typical activated process would be a chemical reaction. Chemical reaction is characterized by bond breaking and bond making. And here you can see a very simple cartoon of a very simple reaction, where on the left side we have, let's say, reactant. On the right side we have products. This in today will be also called like initial state and final state. So these are important words for today, so remember that. So initial state is kind of a reactant, final state is a product. And then when, so in this simple reaction, so we are breaking the bond between the blue and the red atom, and a red atom makes a bond with the green atom. And such a bond breaking and bond making is characterized by an energy barrier. Now, this, of course, is a very simple plot. This energy barrier here appears like a maximum along the reaction coordinate, but actually it is a saddle point. It appears here as a maximum because we use a one-dimensional projection. And now here we have also some other important terms. So the point of the highest energy on the reaction path is the transition state. And the difference between initial state and transition state would be activation energy. And this activation energy would tell us something about the kinetics of the reaction. And this delta E that you see here is a reaction energy, which would tell us something about thermodynamics. And so I know that, for example, the reaction rate constant is given by Arrhenius-like equation, which is written here. So we see that the reaction rate constant is exponential in the activation barrier, and this would be a frequency prefactor. And by transition state theory, this is the formula. Basically, these are the frequencies of the normal modes of the initial state divided by those of the transition state. But for the transition state, the reaction coordinate is excluded because the frequency would be imaginary. Okay, and then if I speak about chemical reaction, obviously chemists use catalysts to reduce the activation barrier, and a typical example of catalysis is a heterogeneous catalysis. And here we can see a snapshot how, let's say, a heterogeneous catalyzed reaction look like. So we have some gas phase species, they adsorb, and then they diffuse on the surface, and then on the given point, they can meet, and they can react, or they cannot. And then some new product is formed, which diffuses, and eventually it should desorb if we want to use this product. And this here, you can see on the kind of a potential energy profile along the reaction coordinate. So more or less all these steps are activated in a sense. So adsorption can be activated or not. It can even be without a barrier. And then diffusion is also characterized by a small barrier. So when a adsorbed species jumps from side to side on the surface, and then we have kind of bond breaking and bond making. When we make a product species, it diffuses, and then desorption is also characterized by a barrier. Now, obviously, potential energy surface is highly multidimensional, but at most we can plot in the computer is a 2D potential energy surface, which is plotted here, and I will use such a 2D potential energy surface plots quite a bit during this talk. And here we have another important word that will be used during the talk, and this is the reaction path. For example, this black dashed line, this would be an arbitrary reaction path from, let's say, initial state to the final state. And then this bold black is a minimum energy path. This is a path, this is a reaction path that is the most probable at a 0 temperature. And now you can really see that the saddle point here, so is so this point at the saddle point, this is called the transition state. And typically in the literature, what you see is a plot like that, which is a projection of this, let's say, minimum energy path along the reaction coordinate. And so we have again this initial state, transition state, and final state. So remember this, I will use this a lot. And then the activation energy and the energy of the reaction. And the acronyms for the initial state, transition state, and the final state are written here. So IS, TS, and FS. And of course, saddle points are unstable configurations. So saddle point is basically a minimum, has a negative, is a kind of a minimum in all direction except one, except in the reaction along the reaction coordinate, it appears as a maximum. And this, of course, is a computationally more difficult task to locate transition state than the local minima. And so here is an example. So this would be this energy profile along the reaction coordinate. And so these points are images, are different snapshots. So here we see initial state. This is nitrogen adsorbed, nitrogen molecule adsorbed on the surface. So here is perpendicular. And so then it tilts down and it becomes horizontal. And such a movement has some barrier. And this here is a transition state. So the barrier is not large. In this case, it is something about 0.3 eV. Now, why is this activation energy so important? I already give a partial answer. It is because it is a very good criterion to tell if a given activated process or a given chemical reaction is kinetically feasible at given temperature or how fast it is at given temperature. Now we can see, if you look at the reaction rate Arrhenius-like equation, that the reaction rate constant is exponential in the activation energy and linear in the frequency prefactor. And so because of the exponential dependence, it is really this activation energy is a good criterion. And for the frequency prefactor, let's say a common value that can be assumed is 10 to the 13 per second. But this is kind of a, let's say, typical value, but it is known that frequency prefactors depend on the reaction type. For example, for desorption, it would be larger. It would be something around 10 to the 16 per second. And if you are interested in typical prefactors for various reaction, you can look at this literature because Danov has tabulated typical frequency prefactors for various reaction types. Let me also say that also the frequency prefactor can be calculated, and you will learn in Friday how to calculate phonons. But today, this talk is just about the activation energy. Okay, now let us just do some example. We have a molecule on the surface whose desorption barrier is 0.6 eV, and now we can ask ourselves what would be the average residence time of a molecule on the surface before it desorbs, let's say at 300 Kelvin. If I plug in the numbers, I would get something about a millisecond with the number of desorption energy of 0.6 eV. If I increase the desorption energy to 1 eV, then the answer would be 10 seconds. And this tells us that, for example, if the molecule wants to persist on the surface at room temperature, then it should absorb stronger than 1 electron volt. Now, another important term today is image, and this is jargon. So what does this image means? Image is a given snapshot or is a given configuration of the whole system. And whenever you will see a point in my presentation, this point does not represent an atom, it represents an image of the whole structure. Now this is a cartoon that I already showed. So this point would be initial state. So this is a configuration of the whole structure. This point is a final state, again, a given configuration of the whole structure. So maybe why the name image? Maybe it comes from a movie industry, I don't know. If you imagine a film strip, so this film strip consists of various images, and each image here is a given snapshot, a given configuration of the whole structure. And in this particular film strip, we can see some bipyramidal anion. So here we can see the two apex atoms of the bipyramid. And so this bipyramid here is rearranging. And at the end, you see that these two apex atoms became the basal atoms. And this was calculated by NEP. And this is characterized by some small barrier. And so remember, image is a given configuration of the whole system. Now, obviously, the potential energy surface is highly multidimensional. If we have n atoms, it is 3n dimensional. But for obvious reasons, when we visualize, the most we can do is we can visualize two-dimensional potential energy surface. And this would be my model potential energy surface for today. And remember, each point here is an image, and it represents a given configuration of the whole structure. I will also use this R. This R vector is not a position of a given atom. It is a 3n dimensional vector of the whole structure, so of all coordinates of all the atoms. Now, in the preceding talk, you heard about optimizations. So you heard how to find local minima. So imagine that we have a given configuration of a structure which would be located on the potential energy surface somewhere here. If we do a minimization, we will find these local minima, because these methods that Pietro has presented, these are methods that find the nearest local minima. For example, for this point, we would find probably this minimum. And of course, finding local minima is today more or less routine, or provided that the code can calculate the first derivatives, it can be done by steepest descent or any other more efficient method that Pietro has presented in the preceding talk. Now, finding a saddle point is more difficult, both from practical point of view, because you need to set up, let's say, a more sophisticated input, as well as technically. And so when I started as a student to do simulations, NEP was not yet invented, and at that time, what we used was a method which can be ascribed as the slowest ascent method, and it was a series of constraint optimizations. For example, it consisted of two main parts. It was kind of stepwise stretching the bond. So you stretch a bond a bit, you fix the bond length, and then you do constraint optimization, and then you repeat the process. Now, for some reactions, this may work well, but for other reactions, it can fail badly. And here we see a snapshot where it fails badly. So if this is a bond length, and this is another degree of freedom, if I stretch a bond, do a relaxation, stretch a bond, do a relaxation, and I continue that, you see I would completely miss the saddle point. And so a method that can deal with such problems is a NEP, which means nudged elastic band. And here are the references for the NEP. And so what is the main idea of the NEP is the following. So we take two local minima, let's say initial state and the final state, and then I connect these two minima with the elastic band. And then the recipe is that we relax the band or with orthogonal forces. Now, what do I mean with the orthogonal forces is pictured here. So I have this elastic band, a given point, and this is a tangent to the elastic band. And then this would be kind of perpendicular force component and a parallel force component. And so here I am optimizing, I'm relaxing this band with this, let's say, orthogonal forces. And this is the equation how this is done. So when I do that, what is going on is something like that. So the band will start to relax. So we also assume that this elastic band is super stretchable, so there is no corner cutting. And soon or later, we will find a minimum energy path, which is characterized by zero perpendicular force components, and then this would be a saddle point. But obviously, this was only a thought experiment, because in computer, for obvious reasons, the elastic band needs to be discretized into several images. So I have then several images instead of elastic continuous band, and then I relax these images with the forces that go perpendicular to the reaction path. But there is a problem with this path discretization. Now imagine here I have this reaction path. These are images. This, for example, is let's say initial state. And suppose that the force components, the perpendicular force components, are pointing in this direction that are plotted in this figure. And then in the next iteration, the reaction path would be something like that. And now you can see that this inter-image distance is not conserved. Now you have this L double prime, which is longer than L prime, than L. And this can cause severe problems. Okay, in one iteration, maybe this is not a large difference between inter-image distance between different images, but after 50 iteration, we can end up with the catastrophe. And so the solution would be to connect images by springs. And this is plotted here. And so we just allow these springs forces to act along the reaction. What has happened? To act along the reaction path, and this would be an equation for the spring force. So basically what we do, we have this tangent, which is along the reaction path, tangent vector, and then we just evaluate the inter-image distance. And here you can see that the distance between these two images is larger than this one. And so here we have large number minus smaller number, and the tangent vector, which means that the spring force would go in this direction and would try to keep the images equidistant. Okay, so now we are ready for the whole map recipe. So it goes like that: connect two minima with a guessed reaction path, and often this can be linear. Discretize reaction path into several images, connect images by springs, and then minimize reaction path using the NEP recipe. And the NEP recipe is the following. So the true forces, that is the minus the gradient of the potential energy surface, are allowed to act only perpendicular to the reaction path, whereas spring forces are allowed to act only along the reaction path. And this is called nudging. And this is why the method has the name nudged elastic band. And here would be the equation for the force that is acting on a given image. So we have a true force which acts perpendicular and spring forces which acts parallel, and this would be the equation for the two components. Okay. Then it turns out that the choice of the tangent is basically would be the direction of the reaction path, that it is crucial for convergence. And a good choice is a local tangent taken only with respect to the adjacent image that has higher energy. And here would be the equation. So if the energy of the image I plus 1 is larger than the energy of image I and I minus 1, then I just take the difference between image I plus 1 minus image I, and then of course I normalize the tangent. And then the most important point in the whole reaction path is the transition state, which is the saddle point on the map. And so one would opt to have a higher resolution of points around this transition state, and one can do that with the variable spring constants, which means that the higher is the energy of the image, the more stiff spring constant it has, and this will make a density of images near the transition state higher. Okay, but even with that, and even if I use many images, I still may not be close to the saddle point. And so the solution is a climbing image NAP method, where we let the highest image climb up the reaction path. And climbing up the reaction path means to inverting the force component that is perpendicular to reaction path. And of course, this climbing image is decoupled from the springs. And here would be the equation how this is done. So we basically invert this parallel component to the reaction path, and so the image climbs up. Okay, so there is another aspect which is very important. It is the initial guess, and the default is linear interpolation. Now it is unfortunate that in this picture, which is a simplified cartoon, the linear interpolation really passes very close to the saddle point. But in reality, in real examples, this is seldom the case. In Quantum ESPRESSO, we can use something that is called intermediate image. An intermediate image is used to steer the initial guess of the reaction path. So we use chemical intuition, and then we can put, for example, here 2 intermediate images, and our initial guess for the reaction path would be something like that. And then, of course, the image with the highest energy, which in this case would be this one, would climb up the potential energy surface. Now, let me quickly go to the structure of the NAP input file in Quantum ESPRESSO. It consists of 2 parts. One is specific to NAP. This is the path input, where we specify these, let's say, variables associated with the NAP. And the other is the engine input. And these are the keywords, and this is the PWX specific. And so this path input consists of path namelist, and also there can be a climbing images card, but only when the climbing image scheme is set to manual. Now, here I have a bit longer input. There are some variables, and now suppose that you are interested of what this particular variables means. So what we do, we go to the NAP description, and then we click a given variable, and we get the explanation. And now it comes this engine part. Basically here we have, this is the PW specification, and these are the mandatory cards and name lists that are always there. And then it comes the specification of the images, which is slightly different than in PWX. So it starts with begin positions, end positions, and then we specify first image and last image. This is mandatory, but we can also specify intermediate image, and there can be one or many of them. Now here is the explanation of some input variables for the NAP input. There are 2 string methods. One is NAP, which is the subject of today. The other is SMD. And please don't ask me about SMD because I have 0 experience about it. I never use it. And so one of the most important parameter is number of images. So how many images we will use. Then is the path threshold, which is the convergent threshold on forces. The number of steps for the optimization. And this means, so in NAP, what we do iterations. So first we calculate, in iteration 1, we calculate all the images. And then we evaluate forces, and then we do iteration 2. We again calculate all the images. And so this number n step path means how many iterations is there. The optimization scheme is how we will optimize which optimizer we will use for NEP recipe. Can be Broyden, can be Quickmin, or can be steeped descent. And this Broyden and Quickmin was already described by Pietro. And for Quickmin, which is our dynamics, we need to specify a time step. Then we have a climbing image scheme, which can be low climbing image, auto, which means that the code will pick the image with the highest energy and will treat it as a climbing image, or it can be manually specified. In this case, we need to provide climbing images card. And then we can specify variable spring constants, and we can use freezing. And this use freezing is, what it is, it is the best to show the example what it is. And this is shown in the next slide. This is the structure of the map input file. So here you see in iteration 10, it calculated image 2, image 3, image 4, image 5, image 6, image 7. So there was basically 8 images. The climbing image scheme was auto. You can see here climbing image equal 4 because it has the largest energy. And here you can see this frozen. So you can see that these 3 images has much larger error than the rest images. And so they are not frozen. This means use freezing. So they will not be frozen in the next iteration. Because it's better, it is convenient first to optimize the images that has larger error on, that are larger away from the minimum energy band. And so in the next iteration, the code does not calculate all, but calculate just those with the largest error. And then in this next iteration, this image has much larger error than the rest, and only these will be then optimized in the next iteration. Okay, now NEP calculations may be relatively difficult to converge, so experience is a plus. And now I would like to give some practical guidelines based on the experience. So one should use, it is beneficial to use chemical intuition to guess a reasonable initial reaction path. And so this entails that you should start from the relaxed initial and the relaxed final state, so that you know your geometry of products and reactants. And then it is a good idea to use intermediate images. This is where this chemical intuition can be exploited. And so that's why this last optimization option is discouraged, because this means optimization of the first and last image on the fly during the NEP run itself. And then the use of intermediate images. So imagine this is an example. Imagine we want to dissociate a molecule at the surface. So this would be the initial state, and this would be the final state. And so if we do linear interpolation, it would be something like that. But this is chemical, not sensible, because we know that dissociation will be something like that. The molecule will first arrive close to the surface, and then it will start dissociating. And if I use such an intermediate image, I would steer this initial guess, and this would be much better initial guess than this one. Okay, and then many times the question pops up: how many images should I use? And the answer is it depends, but usually inter-image distance in the range from 1 to 2 Borg should be okay. And in order to get the idea of inter-image distance, you can do a dry NEP run by setting n step path equal to 0, and then the code will just print for you the inter-image distance. So you see, it takes nothing to do a dry run. Okay, sometimes there is a question: what is this inter-image distance? Basically, this is a distance in 3n-dimensional space. It's as simple as that. Okay, and it is a good idea that you visualize reaction path before you do a calculation, and this is how you can do it. Okay, it is good always to start, because it's easier from the user perspective to start just one elementary step. It's just one settle point, because in principle we can study several settle points simultaneously. Use freezing is beneficial. And then another question: which value of spring constants is not that important? It's not that important. Defaults are just fine. And another issue with the climbing image method: do not activate climbing image from the start, because before this reaction path gets close to convergence, it can happen that in one iteration it is one image that has the highest energy, and then in next iteration, it is the second image that has higher energy, and then this can oscillate back and forth, and this is a recipe for catastrophe. And so the idea is that first you need to relax a bit the reaction path, and then you plug in the climbing image, and this would be a PWTK workflow, how this can be done. So first do no climbing image up to a given threshold, and then you restart the calculation, plug in the climbing image method, and then go to a full convergence. And then the last thing is when you specify atomic structure, do not swap the atoms. So the atom indices should be the same for all specified images, and the only way to demonstrate what I mean by that is to show you a real example. And this is now here. So I have, this is the example of today's exercise. So it is a dissociation of a molecule above the surface. So this is how it goes. So this is the initial path. And now all the indices of atoms are okay. Now here I have the input file. And now suppose I swap two atoms. Now what would happen is this. You see? And this, of course, is not a process that you want to study. So this is what I mean. Do not swap the atoms. Keep the indices of atoms consistent for all the structures. So that's all, and I think it's time to do to try that during the hands-on session. So thank you very much for your attention.
Thank you, Ton. Thank you very much for this very nice presentation with a lot of hints, and it was a good idea to put some self-questions and self-answers here. And actually, there was some questions already that you addressed in your last slide. So is there anyone from the audience that want to raise his hand or her hands to ask some question? So there is one from Dorie Esteras. You can ask, please.
Hello, thank you for your wonderful explanation. Also, I forgot to thank Pedro de Lugas for also his excellent talk. For me, to see how a map between two local minima could be established is something really exciting. So you mentioned that in the case of chemical modifications of the structure, but I'm really curious of if this could be done in something more physical, as for example, materials which have different phases under pressure, or maybe this is a little out of the topic, but in the case of materials that have different magnetic transitions, because it would be really beautiful to see, for example, how a ferromagnet could be transformed in an antiferromagnet state in these pictures.
This is a tough question. I don't know whether I'm able to answer it, but maybe it's related to something that Pietro mentioned before. For sure, I mean, I never done this, so I do not have the idea how I would do that. I don't know. So maybe Alessandro, you are an expert on magnetism.
Well, here actually, I don't think there is a method for the NEB applied to magnetic system, but in some way you can simulate it by using some constrained magnetic moment approach. So in principle, you can locate your initial and final states. You can build a path which connects a path in a spin space. So you can try to rotate a magnetic moment by forcing them in some specific directions. And then you can calculate the energy along this path. In this way, you may have some kind of transition path. Of course, I'm not sure that you can get the lowest one along the path, but it's anyway an energy profile that you are going to explore.
Okay, thank you. I'm sorry, I know that this was a little out of the topic, but for me it would be wonderful to see, for example.
We can discuss more in the next session for the magnetism.
Thank you.
Okay, so let me see. I think there is some question from the streaming. We have some more minutes. any differences between activation energy and energy barrier in calculations? Can we use optimized intermediate images to refine transition states? And intermediate images to be used can be obtained by dry run?
No, intermediate image cannot be obtained by dry run. So you have to, like I showed the example with this dissociation of a molecule, you need to exploit your chemical intuition. You need to have the idea how the reaction how this progress of the reaction would go, and then you just construct these intermediate image structures. Now, of course, intermediate image is not a local minima. Maybe perhaps you can do a constraint minimization, but I don't think this is really something worth doing, because anyway, intermediate image will be used just an initial guess for the code to guess the reaction path. And then the code will generate these images for the first iteration step. It will do piecewise linear interpolation, like I showed, right? And then these images will be relaxed by an Ab recipe. So I think it's not needed that you do a separate, let's say, constraint relaxation of intermediate image, because it's used just for the initial guess. It's used to steer this initial reaction path, and then images will be anyway relaxed using recipe, Ab recipe.
Okay, thank you very much for this explanation. So I think we can stop it here, and let's thank both speakers again, Pietro and Anton. So for those who are attending on Zoom, they can join the Slack channel, and then for the streaming participant, we will recombine at 10:30. Thank you very much. See you soon.
Thank you.
Ciao, hello to everyone. Alessandro?
Ciao,
Yes.
Ari. I'm here. Yes.
Hi.
Yeah. Can I just try the sharing?
Yeah, you want to try your screen, right?
Yeah. So
But
this
I
morning.
think now the problem is that if you share your screen, we project it on. Okay, so there's okay. You can try now, I think.
Yeah.
Yes,
I'm already a co-host. Thanks.
Because the problem is that now these tests are live in streaming, right, Massimo?
Yeah. So
okay, anyway.
just I would like
everyone
just
is
to let you
hearing
know.
and seeing.
Okay, live,
so,
yeah.
Okay.
But actually, on the because I opened the YouTube channel, so I will see how it looks like.
Yeah, do it.
Yeah.
You can share.
So,
consider that
let me
on
see.
YouTube it will take 2-3 minutes to refer to.
So it's
a bit delayed.
yes.
Yeah, because when I came this morning, I had to reboot this machine. It was stuck. So I hope everything will go fine.
Okay, so here it looks good.
Yeah.
Yes.
So here we go. So and then if I go to check. Yeah, so I can do horrible things. I'm already sharing the window, not the whole display, so I can go to a different place to. For example, on Slack, I can go to different.
Yeah, even on YouTube now you are online.
Yeah, I see, and it keeps the so it seems to be working. I hope everything goes fine. I also noticed that this is a 4-year-old Mac. I think 4 cores. iMac.
If you don't mind, actually, you can leave this presentation on. So we have a screensaver for the streaming. Otherwise, we project ourselves in there. So if you leave it, it's better.
Ari.
Yeah.
You hear me? So I ran out of time to make a demo for the remote usage. So please.
No, it is. Please don't worry. I mean, I'm totally fine with that. Sorry, now I had to see where do I find the buttons.
Yeah. So please tell them to pay attention to this how to remote usage.
Yeah. And I checked it also myself this morning, and then so my plan would be so if no one minds, I will quickly mention this also if the tutors are listening. So I looked at the presentations the last days, and I decided that at the beginning I will try to lead the session so that we do the exercises. And when they come to the more complicated ones, then I would go quickly and let them do with you tutors the other.
Yes,
so
we also have to remind that if now we use the remote commands, if somebody has technical issue, instead of writing in the channel of the day, they should write on the channel of the cluster.
Yeah.
Okay.
Which is named cluster dash ICTP, or let's say CISA.
Each of the three
ASI,
clusters.
Like on those channels.
Yeah.
So maybe you can.
You can see how it goes.
Yeah.
You can say these things.
In the beginning.
Ari,
yeah.
Please make a remark that there are some specifics for RNS and CISA clusters. And
I think it's better that I tell it to everyone that on all the clusters, because otherwise people might get a bit confused. So I think it's better that they use the remote SQ, and only when it's finished then they copy everything. Not that they indeed.
To make the because they were doing the copies to monitor the status of the job.
Yeah, and I think this anyway. I mean, it slows down. It can slow down the network or something, and
it can also mess up the Slurm server actually. But
I just noticed the remote SQ is funny because if I may demonstrate it. So if I do remotes, SQ, it actually goes to background. It looks like it's waiting for the output, but it is actually finished.
This is because it goes to the machine, it queries this, and then it returns, and this is standard output.
And it's in the background, right? It's forked. It doesn't wait for the return of the command. So this is just to note them that
press enter.
I thought first though it takes very long, but indeed,
they should press enter. They should press enter.
And then once the job is gone, then they will have it. So I think I hope it's fine. Any other issues? And Tone also, and the tutors, if you have any issues also during my presentation, please don't hesitate to interrupt if I forget something.
Okay.
So my idea was that maybe it's too confusing if we go directly to the remote commands, then we go to the local machine, and then we go to the remote. So I thought that we just skip the first slides at the beginning. We do this on the virtual machine, the first exercises, like it was planned, and only VC relax the zinc scan. That's the first one to run remotely, right?
This takes a while, This takes a while,
So here, if they start, so these two jobs, and of course this one, then at this point we would explain the remote usage. So it's a bit going back and forth in the instructions.
But it's fine. We are all here, so we'll follow up.
So I think it's...
Pietro, there are several questions unanswered on the Slack channel of today. If you can have a look.
Okay, so everything works fine. So I leave the slides. I will quickly run the restroom.
See you in 10 minutes.
Yes, 10 minutes, yes. Ari, can you hear me?
So since I can use the channel, I see that someone is already running the calculations, DFT-D3, dispersion force, and so on.
Where?
I see on the Slack day 3.
Ah,
so you're free to launch the jobs, but I will.
Ari, I just wanted to ask if we had if you can just for the labs, if you can slow down a little bit compared with other sessions. A little, I mean a little, not much, but
because I mean just for the because everyone is listening. So
anyway, there are all the registration and stuff, so it's not a big problem. But
so I mean, to be honest, I have been a bit confused. In the program, it's marked 2-hour slots for the exercises. So I don't know if it was meant that everyone has finished running the exercises in those 2 hours, and so that the tutors, everyone is prepared to take time off after these 2 hours, because it's very short. So
yeah, but we are still following after that. I mean, it's not a problem.
Sure. And then
for example, us on the SCTP, the reservation is up to 4 p.m. So we have like 4 hours more.
I think after we can go into breakout rooms, and that people that have issues can join, so we can leave it open for 1 hour or 2. So for those that have issues.
This is just, I got a bit confused because in the program it's written 2 hours. So so my plan was indeed to go at the beginning slower and synchronized, and then see that the remote commands is working for everyone, and then maybe spreading a bit more freely, and the tutors can help them more individually, so that it will be a bit more individual in the second half of the exercises, because it will be anyway running WTK, and that was done already yesterday.
Yeah, but as Matic is perfectly reporting, I mean, at the end, what we can do is that we can either leave one link Zoom open, and I mean, if we are following some in the afternoon, we can join that link eventually.
Yeah. So I hope that the tutors don't mind hanging
to stay a little bit
for longer. That's what I was most afraid of, that if everyone thinks, okay, 2 hours and then it's over, then everyone rushes. Also the participants, it's very short, 2 hours, I think, at the beginning of learning code. So this is my experience, that usually I would at least need 3 or 4 hours to have more time also to think, and have more time to look at the output and so on. So I will try to slow down a bit. And
shall we start? Jan?
Yes, sure.
Ready?
Okay, so welcome back. Now there is the hands-on session. So the speaker of this session is Ari Pravo Seitosen, and he will introduce optimization, NAB, and automatic workflow. So these sessions, actually, there are also other tutors, Matix Bobernix, Unmesh Mondal, Felice Conte, and Tao Jiang, that will assist the participant for the exercise. There are some technical details that now I leave the word to Ivan. Ivan?
What?
Okay. Okay. Do you want to say something about Slacks and...
Yes, I wanted to say that since now we are going to use, for the people that are following on Zoom, since now we are going to use in this section, we start to use the cluster. So we start to use the HPC resources with these remote commands that you find in the script collection. If you have technical problem using this command, please write on the appropriate Slack channel. So if you look at the Slack channel we created, there is one channel called cluster ICTP Argo, which is the channel for the people that have problem running on the ICTP resources. There is a channel called cluster JSI Harness, which is the cluster for those that are using the resources at the in Ljubljana. And then there is the cluster SISA Ulisse channel, which is the one channel for the people that will use the resources HPC at SISA. Okay, so if we behave this way, we can keep the request appropriated to the correct channel, and we can keep the main channels clean for, let's say, scientific discussion.
Okay, thank you.
You're
welcome.
welcome.
For the explanation, and I think Hari, please, thank you.
So thanks to everyone. Thanks to the organizers for giving me the opportunity to guide this session. Special thanks to Tone, who has been helping a lot setting up this exercise, and I think it also originates quite a lot from the previous edition of the school. So I'm very thankful for also the tutors, and yeah, thanks Alessandro for the introduction. So my name is indeed Ari Pravo Seitosen. I'm working currently at the École Normale Supérieure in Paris, and I think my first encounters with Quantum ESPRESSO were maybe during my PhD time, which was last millennium. I mean, still when it was not pre-code, but so I've been working or using it quite a long time, but maybe a different aspect than what you see today. So please feel free to post the questions. So as you have learned, please use the Slack channel, preferably the day 3. And as Ivan mentioned, if you have any problems with the cluster, post on that channel of which you are assigned to the cluster. In principle, every one of you was already setting up the access to cluster. We were testing that on Friday, day 0. If you have any problems, then please write that on that cluster section. So I guess that the tutors, they are following those questions also during my presentation. So the topic you have seen, it's about structural relaxation and the NEB, and then we will use more and more the PWTK also during this session. So the topics will be the structure optimization. We start with the relaxation of the atomic positions only. You will see the examples. Then we go also to the variable cell relaxation. So that will be the easy ones. And this is what, well, I would say most of the time people are doing. Then we go to the NEB method. And as Tone showed this morning, then this is, sorry, morning for us, maybe another time of day for you others around the globe. So what Tone was showing, how we can get saddle points, reaction paths, and so on. So we will have 2 very simple examples here in this part, and then all over the way, actually already before, we will have examples on using the PWTK, and we go more and more, well, let's say more and more also to the analysis toward the end. So this example 4 will be about some more specific features of these exercises. And then before we really start, I hope everyone remembers to do this git pull. So just to make sure that you have the latest version. For example, this document was still modified yesterday to this presentation PDF file. And if you had these modifications on some input files, if the Git pull complains, you can try these 3 commands. So if during day 1 or day 2 you had some changes, you might change or execute these commands instead of just Git pull. So you should be then up to date. If you have performed, if you have any problems, then please report. So the next slides will actually be about something that we will use a little bit later. So I thought that we leave these, we don't go through them now, but in maybe half an hour or so. So first we go to simple exercises, and then we will use these remote HPC clusters. Like I said, I hope everyone was there on Friday. If not, then you managed to get in contact with someone, or you managed by yourself to set up the access to these 3 clusters. So you are assigned to one of the 3 clusters. So we hope that this works for you from the beginning. If not, then we will see with the tutors how to fix your problems. So we will come to these slides a bit later. The first exercises we will still run on the virtual machines, or if you have set up everything on your personal machine. And these are very simple exercises. These should be very fast to execute. So the first one is a derivation of something which looks like the graphene, but we modify it a little bit. So if you have well, sorry, I show you again. If you don't remember, you can go directly to the link on day 3. You click, and well, the hands-on, it's there, so you can open the file if you want. You can always, like Tony and others have explained, in every directory there's this README file, and then there's some other instructions here for the remote execution. So I have this PDF file which I was showing open already. So now we go to the first exercise. So if you click, you go into this directory on the file browser. You click on the right, you can open in terminal. So you directly come to this directory. You see it's the example 1. So we start here, and as usual, you can start by looking at the structure of the input files. Now there are 4 input files, but we start with the graphene one. So actually, there's the graphene 1 by 1, kind of just for reference, but you can have it look later if you want. So we'll now launch, or I will launch the code. I mean, I could reduce the dimensionality. Now you see what is the difference. If I don't reduce the dimensionality, then you see some atoms are above, some below, but maybe it is easier if in this case, sorry, I go back and we reduce the dimensionality, then it's clearer for you. So I reduce the dimension to 2D because this is a 2D system, and in the third direction, there's supposed to be enough vacuum so that these layers are isolated from each other chemically. So this is the structure. I will make some multiple copies of it just for the visualization. So the computational cluster will be just 4 atoms, but I show how it looks like. So this is the graphene plane. And as you probably all know, in graphene, you have this sp2 bonding. Now, if you put hydrogens, you kind of put the hydrogen where there's this lone pair pz orbital, so out of the plane orbital. And it is actually quite easy to understand that it's easier or better, it's preferable energetically, put the 2 atoms alternatively. So you put every second atom above, every second below this plane of the atoms. So we start from the flat plane of graphene, and then we will see what happens. So this will be the target to optimize the structure in this exercise. So that was the structure. Now let's have a quick look in the input. I mean, by now you are almost experts in the looking at the input. So now we have the calculation mode is relax. So this one, actually, I should mention that in this one, we are still keeping the lattice constants, lattice vectors fixed. This should be optimized. I see there's someone who is writing on the screen. So we should relax also the lattice constant, but this, to be things simple, we don't do it yet. Normally, in almost all kind of systems, you want to optimize the lattice constants or the lattice vectors, let's say. So then in the system section, we have a hexagonal system. So graphene, you have seen it already. It's a hexagonal one. So we have here we use the convention of using the LDN variables. So the first one gives the lattice constants. This is in hexagonal case. Now the lateral lattice constant, and this is in Bohr atomic units. So this is actually something like 2.5 Ångström, I believe, if I remember correctly. And then in the other direction, perpendicular, we have, well, hopefully enough vacuum. So this is actually COA. So the length is 3 in the direction perpendicular to this plane is 3 times the value of this one. It is probably not enough, but this is to keep the calculations fast enough. So we have 4 atoms, 2 types of atoms. You see carbon and hydrogen. And then today we are not going to spend any time on optimizing the parameters. So we have chosen some predefined values for the cutoff energy K points and so on. You are now experts in choosing them. I must say that this might be a bit too low for some of the exercises, or certainly too low for some exercises, again, to keep the calculations fast enough. So if you would repeat this for a real scientific project, you would probably test all these and, like I said, converge lattice constant and so on. Then yeah, we have 2 kinds of atoms. We are using the ultra-short pseudopotentials, and we have the 4 atomic atoms in the unit cell. And now we specify them not in the crystal coordinates, but in the allied coordinates. So all the coordinates are now in units of this value, the LDM1. So you would see that in this case, well, this is how you represent the honeycomb lattice of graphene. So this is the value. This comes from, is it 1 over square root of 3 is the value. And then you would multiply it with the allied. And you saw it already in the input when we visualized it. So that gives the honeycomb lattice. And the positions are so that one of the hydrogens is just above the first carbon, and the second hydrogen is just beneath the second carbon in the unit cell. So this gives this alternating pattern, and this actually keeps also the very high symmetry of the lattice. So then we use K points, like I said, we keep them fixed today. If I may mention some historical remarks, I mentioned my PhD. So actually I was studying the translations of the K points. And now in this case, in the hexagonal cell, it's well, it's not obligatory, but it's much better to use the no shift, so-called no shift. So that's a historical. There was a discussion in the literature why there should be no shift, and that's actually to have a more symmetric set of K points. So this means that there's one K point which is at gamma, and then with this no shift, you will have a symmetric set of the K points. If you would use 1, 1, well, now there's a vacuum in the third direction, so in principle it doesn't matter if you have anything between 0, 1. But if you would put here 1, 1, 0, then you would see that the K points, they look a bit funny, so they will be symmetrized, but the original or the idea is to have the equidistant grid, and that's achieved without the translation. So that's why we have 0, 0, 0, basically always when you have a hexagonal cell. If you want to, you can check my PhD thesis in the appendices. I show how funny those look if you do the translation actually. And then we use the 991 K points. It's again maybe not enough for graphene itself, for this so-called graphene, where you had this hydrogen. It's probably enough because you will see how the electron structure is different. So this is the input file very quickly. So then you can follow the instructions either in PDF file, or if you want more detailed ones, so you can have a look in this file. So this is the README file for this exercise, and the first exercise, here's the command to execute. And now, sorry, I forgot to mention, so the idea is now in the first exercises we will synchronize. So we try to keep sure that most of you, or every one of you, can follow the exercises. Then in the second half, after we have done this remote cluster thing, so then we leave you more freedom. You can take your time, and you can discuss with the tutors. I will of course be available, but at the beginning we try to keep you synchronized. So if you have any problems, please write immediately, and we and the tutors, well, me and the tutors, we can check if you have any problems. But this should be very simple at the beginning. So I hope we can keep everything synchronized. So here we did the execution of the command. Sorry, I make it a bit bigger. So this is just now we still run only with one core on the virtual machine, so a host machine. You could, if you have enabled multiple cores, you could run even parallel. I did initially. I ran some of the examples. I think parallel on the virtual machine. It depends on which kind of computer you have. So I launched the calculation. It's probably very, very fast. So it's very similar to what you have done before. So here it says running on one processor. It means on one core. So there was no MPI. And it was not compiled with OpenMP, no threading, and so on. So again, there's the standard output, or the normal output. You see the repetition of the most important variables here. And then the lattice vectors and so on, the pseudopotentials, k-points, so something that you have seen before. So now doing the relaxation, the output looks very, very similar as before. You see the system, the electron structure converges in quite few iterations. So it goes basically exponentially. So we need only 8 iterations to reach the convergence. And then the eigenvalues, you see, and then after the first step, or the first self-consistency, you see these forces. So these in principle something new. You might have seen the forces before if they were enabled in the output, but now of course the code has to calculate the forces, and Pietro explained this morning how they are calculated using these derivatives of the total energy with respect to the atomic positions. And the good thing, or one of the great things with plane-wave base, is that the forces, they come almost for free. So byproduct, once you have the self-consistency, then it's very fast to calculate the forces on all the atoms. So those are, if you do relaxation, those come pretty quick, all the forces on all the atoms. And here you see already that the forces laterally are 0. So in the hexagonal cell, the xy, and is a lateral plane, and these are 0. Well, you could ask, well, how come they are 0? Exactly 0 to so many digits? Well, of course, the answer is maybe obvious to you. The symmetry is so high that there are no forces lateral. So the atoms in the graphene, they feel no forces because they are symmetric in this honeycomb structure, and there's no lateral force. But we have forces vertical, and then in this, in the quantum ESPRESSO world, you know, these are the forces. It's also written here. They are in the Rydberg atomic units. So this would mean roughly that this would mean that if you displace one or this atom vertically by one Bohr or one atomic unit, the AU, then you would gain or you would lose 1 Rydberg, and that's quite a huge force. But Of course, the forces, these initial forces, they depend on the initial geometry. If you start from something which is very close to the final geometry, the forces will be small. Fine. So here, now it's written, so we didn't specify anything in the inputs. As Pietro explained this morning, this means that we will be using the BFGS optimization algorithm for the geometry. And it says, okay, now we have done one self-consistent cycle, and this is the 0th algorithm or displacement of the atoms using the algorithm. So after that, the atoms are displaced according to the forces, according to the BFGS algorithm, and we go to the next self-consistent loop. And now it converges, well, in 7 steps. Again, the eigenvalues, the forces, you might notice, okay, the forces were 0.2 something in the first iteration, and now they're 0.1 something. And this was the second self-consistent cycle, and we have accomplished the first BFGS cycle. And we have the new atomic positions. Okay, and we would see that, okay, these forces are still too large. We cannot consider the structure converged. So that's the third iteration. Forces, again, smaller, 0.0 something, and the new positions. And this continues. Next one, next one, next one. And now, actually, the forces have reached the convergence criteria here, which I mentioned here. And I think these were the default values. We can, of course, give these in the input if you want the stricter convergence criteria. So you can change those in the input. And then we have this section, which you see now it says something about final. So these are the final coordinates. So these are the coordinates that are the end result of the relaxation. Now we see the position of the atoms. We will use the X with 10 to visualize this. Now we use the output file, of course, and we had to modify the option from I to O. And again, I reduced the dimensionality. This is just for convenience in how to see the structure. Now you see we have these 4 options. We can take the initial coordinates, so this would be the same as were given in the input file. We can use the latest ones. Actually, they are in this case the optimized coordinates. This is because the calculation has converged. That's because we have this final section around the latest set of coordinates. During the run, one would use this latest one if you want to see the latest one. But actually, we can also have a look at all the intermediate ones also. So we can choose the last one, and we visualize this. And then you get this animation control. And these 6, it says slides. So these are the different geometry relaxations that you can also kind of display them as a movie, but now we just look them one by one. So it always starts from the initial geometry. So you remember this was the flat one. We started from that one. So if you click on the arrow, a single arrow to the right, so it says next image. So this was the initial geometry, 1 out of 6 geometries. If you click the next one, or the arrow to the right, so next image, you click on the second one, third one, and so on. And with this rightmost button, you come directly to the last current slide, which is the last one, so 6 out of 6. So this is the 6th geometry, and this is actually the optimized geometry. And what you see is that now the 2 atoms, the carbon atoms, they are no longer on the same plane. And this is what you could also see from the atomic coordinates, the numbers. So they have displaced them vertically. And of course, the hydrogens, they follow the carbons. And what this looks like is, so I just show a bit more of these cells, how this looks like. It's like in the PDF file. So every second pair of these CH atoms is going up, and every second one is going down. Now the question will be, why is this? And I mentioned already something about the chemistry at the beginning. So sp3, if you think of sp3 hybridization, That's of course the tetrahedron. Again, in graphene, you don't have anything below the plane, and the carbon takes the sp2 hybridization, and it's perfectly fine there. It's a semi-metal. Here we have sp3, so it's like a silicon bulk would be. And so we have somewhat out of plane organization so that we get a bit closer to the geometry like that would be in a tetrahedron. So around each carbon atom, you have 3. Let me see if I can zoom a little bit. So if you take, for example, this, just a second. So if we would take this carbon atom, for example, and look at how it's coordinated. So it has 1, 2, 3 carbons, which are slightly below, and those are those ones by this translation symmetry, which are below the plane, and where the hydrogen is below them. You remember there were 2 carbon atoms in the cell, so one had the carbon up, the other one down, and by this periodic boundary conditions, these are all 3 around this central carbon atom, and then there's 1 hydrogen above. So this gives the central carbon atom this kind of sp3 hybridization. So it's close to the perfect sp3 tetrahedron. And then, of course, if you would look the same for the other carbon, it's just that it's below the plane, but it has the same. It has 3 carbon atoms above the plane, and the hydrogen beneath it. So this would also show up in the electron structure. Now we are not going to look at that. That was not planned for the exercises. But if you remember difference to the input of graphene, now we actually have commented out the occupation. And this is because we know that this is actually a semiconducting system, or is it even an insulating system? The hydrogen atoms, they kind of saturate these carbon atoms, and instead of the graphene, which is a semi-metal, you remember there's the gap closer at the Dirac point, and you saw the density of states. Here actually there would open a gap, but we are not going to analyze the electron structure. If you want, later you can do this. You can plot the density of states and so on. Now, because we are not using the occupations in the outputs, just quickly repeat that. When we saw the K points, the occupation numbers, these are all occupied states. So no unoccupied states are calculated. So we don't get automatically the band gap from this calculation. So you have to do an self-esteem calculation, or otherwise you have to include unoccupied states. So this, if you want later. So now the idea is to do this relaxation if you haven't launched the job yet. So we wait a while, and we hope that everyone has managed to run this example. So if you have not managed, or let's say we give it 2-3 minutes, you try to launch this calculation if you haven't done it, and then you try to look it in the expression. And please let us know on the Slack, or well, you can also raise your hand in Zoom if you have any problems, or if you have any questions also. So now it's a couple of minutes. Let's take a couple of minutes, and you can try to accomplish this calculation. So let me see. I try to follow. I don't know. Anyone has a question on?
So if someone want to ask some question, can raise their hand right now.
Yeah. So now it's a good time. If you have any questions, problems here, because this is the first relaxation calculation. If you have any doubts or so, you can ask now. We use a couple of minutes for this.
Yeah.
And then we go to the next exercise. Of course, you can keep asking questions, but I think now it's good time. Either launch the calculation if you haven't done it. If you have any problems, please report us so that we we remain synchronized at the beginning of this session. So, and I think, yeah, Alessandro, you can keep track.
Yeah, I will check.
I mean, I don't. Okay, nothing on the chat of the Zoom. That's always good. Anything on the Slack? So there's there's already an answer. Yeah, thanks, Felice. This was the answer. Felicia answered about the XCRIS10. Like I said, you launch, as usual, we launched the XCRIS10. And the first question it asks, do you want to reduce the dimensionality? Here we can do it. Initially, actually, you might, I mean, you can keep running the example. I'm just explaining at the meantime for the others if you have already finished. Initially, it might be a good idea to show, maybe I will show here. I mean, we can take the initial. Now I don't reduce the dimensionality. And I show the optimized coordinates. And now we can have a look. And as I mentioned, it's not that interesting to look in this direction, but something I think it was mentioned or discussed to some extent. So the eternal question is, well, I pose it this way. So even if you have, let's say in the real world, you have a two-dimensional system, you have one-dimensional system, you have a cluster, zero-dimensional system, you need to give these lattice vectors in a quantum espresso. And then the question is, how much space do you give? It was discussed whether some people take 6, 7, 8 angstroms maybe. And then the question is it enough? And it was mentioned that, for example, if you have a dipole in your system, convergence is much slower. So you might have to go to these algorithms which take a weighted dipole. So everything depends on your system. If you have, for example, ions, like some people have studied the absorption of ions on graphene. So if you have this kind of, well, it's a very ionized atom, so it creates a strong dipole if it's only above the plane. So then you probably need much more space also. It depends on really on your system, how do you localize the IO electrons and so on. So here initially you can have a look and get an idea how close the atoms are. And I will not give any value. So you always have to think what is enough for your system, so you can do the convergence check. So
Arim, there are some questions on the streaming. Maybe we can get some question now. If one geometry does not relax, can we reduce the upscale parameters?
Yes. So you can try to make the kind of the steps, at least initial steps, smaller. So if your structure keeps just taking many BFG steps, and if it looks like the structure is not converging, then you can try, for example, to reduce this upscale parameter. I checked, and I think 100 is actually.
So he's also asking what is the reasonable values for this parameter. I mean,
well, the 100 is the default. I think I checked, so this would not be even needed. But most of the calculations relaxation that I have done, they have converged with this value. Again, it depends on the system. In some kind of systems, you might have better luck. Better luck means that you converge faster. So, like I said, basically always I have managed to get the converged geometry. If it's a global global minimum or local minimum, we cannot say. But BFGS, in most cases, it has converged. And then it's more, this upscale is more how fast it converges. So if you need 10 steps, 20 steps, there are cases where I have needed hundreds of steps. And the default is 50 iterations. In the ion section, you can put the variable to increase this. The other option is to make a restart. So you continue from the previous geometry. What I do sometimes is also I reinitialize the forces or the history of BFGs. So I just copy the coordinates into a new input file without doing a restart. Because with restarts, if you do a restart in the control section, normally it also restarts with the history of the relaxation. And what I do is just I start from zero. This kind of forgets the history, because I don't know if it was clear. So
okay, so I think some of the tutors actually can also answer in the streaming chat from YouTube, and
also
and
if you
some
have
other tutors maybe can answer the questions on Slack. while you are doing the exercise, so that we can optimize the question session.
Yeah, so I hope now everyone has finished this exercise. Again, if you didn't.
Okay, anyway, someone is suggesting to slow a little bit down, so maybe you can.
Okay, so is there someone who has had problems running this example? I mean, just please let us know, so we know that we remain synchronized. Just write on the Slack immediately that I still have a problem, and we can have a look together. Is there anyone?
So one from streaming was was saying that getting an error bad option PWI.
Sorry, that's in the.
Well, I don't know what was the step. I'm writing here in the chat of Zoom.
Zoom. Okay.
No, I just reported it here.
Okay.
From the.
So let me see on Slack, day 3. And well, maybe I will not start to read all the if the answers were satisfying. Ludovica Zulo, that's the latest one. Is there a way to get a good trade-off between the energy convergence threshold and force convergence threshold? Again, it depends on your system. I'm sorry to say. So, I mean, you could try. In some cases, I might say, okay, I don't care about the energy convergence. I'm only care about the force convergence, or the opposite. So there's no general. I mean, you can say, okay, in most systems, maybe one parameter is 10 times the other one. I think this is what I usually use. I mean, I cannot, I don't have at hand those values. Usually I try to converge a bit stricter than the default ones. And then you will see later during the week, I think, in the phone calculations, you have to relax very, very accurately, because a small error in the optimized atomic positions might lead to very large error in the calculated phonon properties, so phonon frequencies and phonon modes and so on. And just a general comment. I mean, well, I hope everyone else is finishing, if you haven't done it already. A very general comment about these threshold criteria, and this is very general also on day 1 and day 2. So everyone at the beginning asks, what is the value for the convergence? And it was given, I think, 1 millirad per atom, but the really tough answer is it always depends. It depends what you want to look at. So if you want to look at the phonon frequencies, it might be that the criterion doesn't hold. You have to go to a stricter convergence in the cutoff energy, in the number of K-points and so on. The same is for the forces. There's no general rule. It's unfortunately quite a lot of experience that how accurate do I have to go? Because like I said, for the different quantity, if you just want to relax geometry of, for example, atom, molecule, and surface, it's probably enough quite loose, the default values. But if you want to calculate the wide pressure and frequency of that molecule, then you might have to converge the forces much better. And then, yeah, convergence of the energy and forces is of course related, but there's no direct rule that it's 1 to 1 or 1 to 10 or so. Unfortunately, it's mostly experience. So now I hope everyone has finished the first exercise. I see now there's someone who has been running the next exercise. So that's I will show. So here was this small explanation. There's an image of this system. And then here was the final geometry. So it is so-called buckled structure. So every second atom, there are 2 carbon atoms, 2 hydrogen atoms per cell. And this is then the periodic replicas, what you see in this image. So every second carbon atom is kind of above the initial plane, and every second is below the plane. So this is what we have executed now. So the next exercise is somewhat more, oops, sorry, I confused the keyboard shortcuts, sorry. So the next exercise is then to run bits more, well, let's say a system with a bit more degrees of freedom. And that's studying the adsorption of oxygen. Sorry. Of course, this is an input file. So the next systems we're going to look at, again, I reduced the dimension to here because it's a two-dimensional system. So this is now, in the previous example, we put hydrogen at each carbon atom. And now we are looking at the adsorption of, in principle, isolated oxygen atom on the graphene. And in this case, we have chosen already this supercell. It's mentioned explained in the exercise sheets. So we have chosen 3 by 3 in both directions, 3 by 3 unit cells. This is the so-called supercell. So instead of the 2 atoms that we had in the first case, or in the case of pure graphene, now we have 18 atoms. If you would count, you will have 3 times 3 simple unit cells, and then there are 2 atoms per cell. So 2 times 3 by 3, that gives 18 atoms. And then we have 1 oxygen atom, which is now above one of the carbon atoms. Well, sorry, it's kind of bridging above the plane between 2 carbon atoms. Sorry, I tried to. You see, this is so-called well, epoxy group. So an oxygen with 2 bonds to the hydrogen, kind of creating this triangle carbon-carbon oxygen. And this is a model for the graphene oxides. This would be a long story. So this is one of the groups which is believed that exists in the graphene oxide. So now we took this just as the example for today. So it's absorption of this oxygen and how it creates this so-called epoxy group on the graphene. And we chose 3 by 3. Again, it's maybe not enough. This you would have to do a convergence check if you do all the calculation in 3 by 3. Well, you could even start 2 by 2, supercell 3 by 3 and cell 4 by 4, and then you would check when your parameters that you want, for example, the adsorption energy of this oxygen, when are they converged with the size of the supercell. So now it would not be converging with respect to for K points, but also the lateral dimension of the supercell. This is what you should do before starting this, because again, the oxygen now it's above the plane, so it will create a dipole. It will be partially charged, of course, it is more electronegative than the carbons, and so on. So it kind of creates a dipole, and it's partially charged even, so it's kind of this 1/r dependence on the distance between the periodic replicas and so on. Again, this we don't do today, but you should do that if you do a real project. You should be kind of sure that these defects or these adsorbates are far away periodically, that you are converged or converged to some criterion. I don't know, some 10 millielectron volt interaction between the periodic replicas. Okay, this is the system. This is the coordinates, and if we have a look in just how the input looks like, it looks pretty similar as before. So again, it's a relaxation calculation. Now we had to multiply the lattice constant in the hexagon case by 3, because we have 3 unit cells, and then at the same time we divide this third cell dimension, which was the C over A, by 3, because the A was multiplied by 3. So we can divide this C over A ratio by 3. So now the distance actually remains the same between the planes. And we have, I mentioned 18 carbon atoms and 1 oxygen atom. And we have 2 types, again, because we have the carbon and the 1 oxygen. And I haven't I mean, I have tried to follow the talk so far, but if I miss this, as a reminder for the cutoff energy, if you have several different kinds of atoms, if you have check the convergence, for example, for carbon, you have checked the convergence for oxygen, then you always have to take the cutoff for the highest ones of those elements. So now we know from experience that the oxygen convergence is lower with respect to cutoff than carbon. So you should choose the cutoff value which makes the oxygen converge. It's just a small side note, but now for the computational efficiency, again, these values might be a bit too low, but you might want to check those in real calculations. So otherwise, the input is more or less the same. Now we do use the fraction of occupation numbers or the smearing because we are studying graphene. The oxygen disturbs the electron structure, but as you can imagine, there are 16 atoms of carbon which don't have oxygen just close by. So probably this direct cone, it doesn't survive because we break a little bit the symmetry by absorbing the oxygen, but it will probably remain with the small gap the system, or it might even become metallic. It depends also on the initial geometry. Okay, so the coordinates, now actually we use we give the coordinates in angstroms, not in the crystal coordinates and not in the coordinates with, like in the previous example where we gave the coordinates as a function of the alat. Now it would be funny to use the alat because from the simple unit cell, you remember we took 3x3 supercells. So and we had to multiply this parameter LDM1 by 3. And that changes this alat parameter. So we should change the coordinates corresponding if you're using the alat coordinates throughout. So now they are giving in absolute coordinates in angstroms. And we have the 18 atoms and the 18 carbon atoms and the 1 oxygen atom. Now there's this remark, yeah, we should actually use 3x3x3, but it's a bit too slow on the virtual machine. So we cheat a bit and we use gamma point only. It's certainly not enough. So yesterday you saw we use 9x1 in the case of graphene. Now that we have a supercell 3x3, you can easily verify. That's also a good exercise of the folding of the K points when you go to supercells, that the corresponding K points would be 3x3x1. But, and this is what we should be using if we were consistent. But again, to be a bit faster, we use this only the gamma points. Now you can, if you haven't done it already, you can run this example. Sorry. Sorry. I said, if you haven't done it, you can launch the calculation now. And if you have extra time, again, you can have a look at the output. Of course, the beginning is similar. Now it does the self-consistent loop. So, and now you see the system requires more steps for the initial convergence. So here in the case of graphene, the previous example, we need 8 iterations. Now it took 12. And now we actually have the also some unoccupied states, and because of the smearing, the broadening, and the Fermi energy, so one sees that okay, the Fermi energy is between those two values. Again, this is certainly too little on the gamma points, but this is what we can easily reach on these computers. And again, now we have this smearing contribution because we're using the fraction applications. The fourth is now you see that also we could have checked in the beginning. So because the symmetry is now much lower, there are forces also in the lateral directions. So there are no zeros anymore. So the symmetry doesn't keep any of the forces zero. And then we see, okay, the forces on the oxygen vertically, that's the largest one. These forces, initial forces, they of course depend which kind of initial geometry you have given. So that might be a huge one if you have a very bad starting geometry, or it could be already very small if you manage to start very close to the final or the converged geometry. So the same kind of thing, it shows the first forces. This was the first self-consistent cycle, and then this was the 0th BFGS optimization step. And then the calculus continues. Now we are at step 7. So on my machine, I started it some 2-3 minutes ago. So this indeed, like it was mentioned in one comment on Slack, this example takes a longer time. It takes longer time already because it has more atoms, and the calculation time, if you would have the same kind of atoms, the same cutoff, it converges. The computational time scales with the second, third power, in principle, the third power, the number of atoms. So if you now put 3x3 supercells, so it will be more or less there were 4 atoms in the first case. Now we have 18, so let's say 4 times more atoms. So if we would have the same K bonds, this would be 4 to the third, roughly. So 100 times slower. Now we only use gamma point, but because we have more atoms, in principle, the calculation is already, because of that, it's heavier. And we are, again, as you saw in the beginning, we are only using one processor. So we are following the steps of the self-consistency. Again, we can check the previous one. So 12 steps, and it seems that, okay, between the old and the new geometry, the total energy of the system is changing already very little. So we hope that soon we will be converged. Again, already 14 steps, but I think the forces, well, they are reducing. And usually this BFGS, it's at the beginning, it needs more steps because it's further away from, it needs more steps at the beginning to reduce the forces, and then it starts to learn about the system. Like Pietro said in the morning, it starts to learn how the Hessian more or less looks like, and then it can use this information, and the forces, they reduce then faster toward the end of the calculation. This is the present values of the forces. Again, going down and down and down, but there's still some forces which are too large for the convergence criterion. So in the meantime, while the calculation is running, just to make sure, has everyone managed to launch this calculation? Either it has converged or not, but do you have this calculation either running or it's finished? So please, again, give a quick comment on the Zoom or on the Slack, so that we know that there are no problems running this example. And I mean, it's not, okay, now it just converged. It needed 20 relaxation steps. Again, this depends on your system. It depends on the initial geometry, how far it is from the final one, and so on. So we can have a look on the structure. Again, well, I go first to 2-dimensional reduction of the visualization. We can take, again, animation if you want, or I go directly to the optimized one. So this is also the latest one. So the last 24th step. And this is now the final optimized geometry. And as it would be expected, well, far away from the central oxygen, the planarity is more or less kept. So you see that more or less the carbons are still in the same plane, but then this epoxy group has somewhat lifted out of the plane. Maybe also the second neighbors, but less. So this is, again, it's kind of clear that the carbon, it doesn't want to keep the planar hybridization, so it kind of lifts a little bit to get closer to the sp3, and then probably there are the dangling bonds on the other side. But this is expected that two carbons would also lift with the oxygen. And now, if you want, you could have a look, for example, in the bond lengths between the carbon and the oxygen. So if you choose the carbon, the oxygen, now the bond length is 1.5 angstroms. So that's a very typical bond length. And again, this is in this case of the epoxy group. So by internal symmetry, the other bond length should be more or less the same. And the carbon-carbon distance is 1.45. We can check, we don't have the initial value, but more or less far away, it's a bit smaller. Of course, because the coordination here far away, or in the perfect graphene, it's the sp2. So the bond lengths are a bit shorter to have this hybridization and kind of the electron density around the carbon atoms. And here it somewhat increased the bond length because there's the fourth bond to the oxygen now. So that's why the carbon-carbon bond length is a bit shorter. Sorry, it's a bit longer than in the carbon-carbon bonds without the oxygen. So this is quickly this example. Has everyone finished this by now? So I see there are some questions also about the chemistry. Yeah, Tony has answered. So in principle, now it's a good note from Josef Hannis. You saw that in the first case we absorbed the. Now I have some problems on my machine. Some problem on my machine. Can you still hear me?
Yes, absolutely. Yes.
Yeah, because I cannot change between the desktops on my computer anymore. Something has frozen on my machine, or it's just very, very slow. So I cannot go back to the virtual machine anymore. Okay, there we go. Sorry. A good remark. So the first example, or let's say the 0th example, that was the graphene, which you did also yesterday. It is planar. There's no need for this dipole correction. There's no dipole in the vertical direction. As Tony explained yesterday, if you have two different kind of surfaces, you will have a different potential, or the asymptotic of the potential, and in principle you need this type of correction. And in the first example of this morning, the graphene, we put the hydrogen on both carbon atoms, and because of the symmetry, there's no dipole across this slab. But today in this example, indeed there's a dipole. I mentioned that this oxygen gets polarized and so on. So in the really good calculations, one would indeed put the dipole. So one would put the dipole correction so that it's in between the two layers, so that it doesn't affect this kind of discontinuity, or a step in the potential which is added in the dipole field. It would not affect directly the electron structure of this structure. So that's why we need to have enough vacuum also, that we can put this potential in the vacuum between the planes. And this is again what should be checked. Well, Tone showed that example yesterday. We saw that there was enough vacuum so that the potential gets really flat, and then there's this kind of step discontinuity, and then it goes to the other side of the back side of the slab, and then you have a different value of the potential. So indeed, here one should use the dipole field to make a very good calculation, a good note. Any other comments, questions about this example? Okay, so we continue. I don't know if someone has a step or further.
If you have the chance and you can read the streaming, you might get some question there. I don't know.
Yeah. It's again interesting to read which question has already been answered. It's not in threads. I see that Matic,
yes,
they are already answering. So it's a bit.
Okay, no worries, no worries.
So, any questions now? I mean, you can also raise the hand. We can stop here if anyone has an urgent question until now. If there's nothing, then we go to the next step. So we will go to the case where we also relax the lattice vectors. To be honest, also in the first case, yeah, we should have relaxed. In almost all cases, we should relax the lattice constants. I mean, it's also, there's discussion about strain and so on, so we can also relax with an external strain. So there are a few cases where one doesn't need to relax at the beginning the lattice constants or the lattice vectors. So here, as a reminder, well, sorry, now we go to a case which looks very similar in the lattices. So that's a HCP structure of bulk zinc. So that's an elementary crystal, and zinc crystallizes in the HCP structure. And HCP is exactly what we used before. So that's the IPREV4. You see here the value which we are going to use, it's IPREV4. But now it's different in the sense that now the C value, it's not the 2D material, it's bulk material. So in the third direction, there's the C, and now the C is really significant. We don't just choose it so that we isolate the layers from each other, but in the HCP crystal, each of the layers is interacting also in this third direction. So now the C is really a physical value, and that's, you will see then that in the databases structures, C files, you will see a value for C also. And otherwise, it's quite similar. So the lattice vectors are similar. Like I said, we will be using the IPREV4, and there are the two independent variables, A and C. Now we optimize them both. And there are two ways, two rough ways how to do this optimization. One is the manual way, which is noted here, and that's calculating the potential energy surface. So we will calculate several values of A, calculate several values of C, and then we get the two-dimensional plot. And the optimal values are there where the energy is the lowest. So we will, with this algorithm, if you just calculate the grid, we will probably not hit that value, but we could, for example, interpolate or find a more intellectual way of choosing, of evaluating the exact points where the energy is minimum, and those are the values of A and C that we would have using the approximations in our calculation. So again, the cutoff energy, the K points, and most important, the exchange correlation function. Again, notes here what we will get as lattice vectors, they don't correspond to the experiment. And even if, in most cases, even if you would have most converged cutoff energy, most converged K-point sets, most converged or best possible pseudopotential, or even the hard potential, the Coulomb 1 or R potential, you will not get the experimental lattice constant. And often these are not the values that you want to get, because there's the exchange correlation approximation. So you should get the values which are best converged with respect to your exchange correlation functional. And if it's away from the experiments, well, that's because of the approximation. But you should not compare, oh, I have better correspondence or agreement with the experimental values if I, for example, use a lower cutoff. No, that's I would call it cheating. You should just converge everything, and then those are the values. If you can exclude all the other sources of error, tough luck. That's just the correspondence to the experiment. And usually, well, we are using, in most of these cases, we are using a GGA, and it has been maybe seen already. Usually we are more or less 1% larger than the experimental lattice constant. And I would say 1% is not too bad. And then that's the value which traditionally one would use. There are cases when one uses actually the experimental lattice constant for the real calculations applications. But here we now try to determine the optimal A and C, these values by two ways. The first one is the manual way, and this is just, as I mentioned, sampling the values of A and C, hopefully so that in both directions, the final optimum value will be inside this two-dimensional grid, and preferably more or less at the center. And there's already a ready script, and this we can launch in a while. And this is the PWTK script. You have already experienced some PWTK from the previous days. So this is a way how to calculate. You can calculate that on your local machine. It takes a couple of minutes, or we can use the remote computing. We will now go to the remote computing. If you haven't studied that yet, we will start that with this example. And the second way is this variable cell relaxation. So that's just almost the same as the calculations before. So when we did the relaxation of the atomic coordinates only, but now we change from relaxation to variable cell relaxation. The calculation method changed it from relax to VC relax. And now we have to include the cell name list, even if it's empty. And I will just show the so the first example. So the first way to calculate was this two-dimensional potential in the surface. There we use the SCF. Actually, we could even use the relax, but there's nothing to relax. Due to high symmetry, there's nothing to relax. The coordinates will have zero forces by the symmetry. They will be stressed, but if you do relax or SCF calculation, it would give you the same result because the forces will be converged in the first step. But let's have a look in the inputs with the relaxation of the lattice vectors. So again, the calculation method has been changed to VC relax, and we have included the cell name list. That's basically all. One more side remark, which has probably been made, but to make sure that you remember it. Now we are calculating the stress tensor. So the stress tensor is needed for the VC relax. So Pietro explained that this morning. So this is the derivative of the total energy with respect to changes in the lattice vectors. And this is a higher order derivative. If the forces were already derivative, so this is a higher order derivative, and this actually converges slower with respect to the cutoff energy than the forces. So the easiest to converge with the cutoff, if you increase the cutoff, is the total energy. The next one would be the forces, and the third one, unfortunately, is the stress tensor. So usually you have to go to a higher cutoff energy if you want to use the VC relax. And again, this is then you have to test the convergence. We don't have enough time to explain that fully, but then Pietro already mentioned that, okay, the last step will be done with the new basis set that was calculated or re-initialized with the lattice vectors of the otherwise converged geometry. So you will see that in a while. So this is the relaxation using the variable cell. And sorry, Tone, are you?
Yes.
Yes.
So shall we launch this now on the remote cluster?
Yeah, we can try.
Yeah, so this will be, if you haven't tried to launch anything, so here there are these two steps, the manual step, which is the PWTK script, and then there's this step where you can directly run PWX with this input, And both of these can be run on the remote cluster. So let's try our luck. Now, if you don't remember anything from the day 0, or if you joined a bit later, but let's hope everyone has the remote access. We will now be checking that on the fly, if yes, if not. So at the beginning, after the introduction slides, there were the 2 short introductions to the execution remotely. So the first one is the remote execution of the executables. So here it's a pw.x, and this is now for the input using the VC relax, because that's already input for the pw.x. And if you want to, or when you want to run the pwtk, this zinc-scan.pwtk, you can run that remotely using the remote pwtk command. So how you run those, it's just like before, but you don't provide any output. That's not necessary because this output will be created on a remote machine. So for single input file, you would run remote MPI run, then the executable, and now you have to use the -in option, and then the input file. So in a while you will see how this is done in practice. So this is running MPI run. The second one is remote pwtk, and then the name of script. And then in the output, you will see in a while, in the output, you will see, okay, it will be launched on the remote cluster. On the next page, then there are some, well, if you have other kind of script, you can use also the remote dispatch, but we are not going to use it now. The very important point that Tone has mentioned me is that on some of the clusters, I don't give any names here, but there's a problem with the file system, or problem. It's tuned so that you should better not touch any of the files, not even look at the output, not even copy them before the job has finished. So we ask you, once you have launched your job with this remote MPI run or remote pwtk, you use the remote SQ commands, and you can launch it as many times as needed. And you only go to the next step, so copying the output file. So that's actually on the 3rd page. You only do this after you have seen that your job has finished. These jobs will probably not take very long. I don't remember, half a minute or so maximum. So they will be quite fast. The next example will take, I think, something like 2 minutes. And please don't try to copy any of the files. Don't log in on the cluster during that time. This might cause some damage to the files. So just be patient. You can have, once you have launched a job, for example, you can look at the input file using XRIS, and then every now and then you check the remote SQ. If you still have this kind of line, it says that your job is here, it's running because it's R, and once it has disappeared, your job has finished, and then you can copy the data. So please remember this then. Be patient, execute the remote SQ until your job has finished. It could be that if you make a mistake at the beginning, then actually the job it takes us a fraction of a second on the cluster, and then it vanishes immediately. So even then, what you will do, you can copy, well, all the output file, or even better, you just use the command rsync_from_hpc space and the period, the dot. This will copy all the files from the cluster to their current directory. So in short, you either execute the remote MPI run or remote pwtk with the corresponding options, and then you check your SQ or the queue job if it's still in the queue. Once it has come from the queue, you copy all the files. And I think at this moment, at least, there's no need to copy the files explicitly. So this is done automatically. So please don't execute today the HPC rsync HPC. This is for your convenience for later. And we don't need the remote dispatch today, I think. So let's try that. So we come to the zinc example. Sorry, I went a bit too far. So the zinc example, so the manual way. Let's try the manual way first. So that's a PWTK script. Sorry. So there's this zinc file. So let's try remote PWTK zinc scan PWTK. And we hope for the best that it's working now. Okay, that's just the output. It says something, okay, it's submitted the files to the cluster. You don't need to care about this. And then it says submitting the job. And it says it's using, well, actually not process, but 20 cores. And that's probably too much for this example, but you will see that the next example will be harder. It's better to use those 20 cores. Okay, we check 30 seconds execution time. So it's running because there's R under the status. And it has been running 30 seconds. Now it looks like the output is hanging, but just press enter. It's because the job went, the SQ job went on the background. So you just press this command and you can press enter. So it seems that everything is fine. It's running. It's 1 minute. It's still running. Still running. At this point, maybe you can report if you have any problems executing this. I mean, the other command so this was this manual way, and I think well, maybe it's better to wait until this has finished when we launch the other job. So it's 1.5 minutes now. Then there's this other job we will be launching in a while. If you have finished this first step, and if you have a look at the output, you can already go and you can try out. Sorry, again, I'm almost forgot. So the other way was this relaxation with the variable cell. So this is now executing directly with MPI run, the executable pw.x, and the input file is this zinc with VC relax. This you can submit. I prefer that you submit it only when. Sorry, I didn't do this. I just put this so that I remember. So let's check the queue. It's still running. It's taking more time than I remember. But in the meantime, has everyone managed to launch either the MPI run job or this PWTK job remotely? So please raise your hands in Zoom. Please write on the Slack. I mean, I see also I'm following the stream, but I think yeah, there are interesting questions about the van der Waals forces and the number. I think they will come, the van der Waals functionals, and this will come later during the school. So now we are just using GT8 to keep things simple, but this is certainly a big issue in this, in particular when with this rise of the 2D materials, so between the layers, adsorbates and so on, often, or adsorbates on surfaces and so on, and you have often the weak van der Waals forces. So anyone has trouble? Okay, I still quickly check on Argo. So, and then one important note.
So I start to see a few jobs on the HPC cluster, so that's cool.
Yeah, good.
Means the configuration should be fine. So if you have problems, you can either write on the cluster HPC ICTP or even here. I mean, we can join some breakout room if you have some help.
But I think quite soon I will continue with the example. So if you're in the breakout room, then you might miss the following explanations, but well, your tutor can help you further than, or you just follow the PDF file. So I just want to note, I tell it to everyone because it was a problem. I saw it this morning, or someone had asked already this morning, and now there's during the exercises. So these remote commands you run on the virtual machine, not on the HPC cluster. So the idea here was to simplify your life. You don't have to log on the cluster. This, of course, is not the real life of a computation scientist. You probably have to fight how to log in and so on. But we try to make everything as smooth and simple so that we don't lose time connecting to the cluster and so on. So the idea is that you run all these commands from your virtual machine, or if you copied all the data on your laptop or some other machine, but you don't log in to these 3 clusters to execute these commands. If no one reports any other problem now, so I suppose, I hope everyone has done the calculation. So this was for the 2D sampling, the manual way. And now I copy all the data. So I use this rsync _from _HPC and period. So that copies all the files, at least it should. Indeed, we get lots of output files. So we get, for each combination of the A and C, we get the input and output file. So there are many output files. And you see already the energies, actually, they have been collected in one of the files. So that's also done on the cluster at the end of this job automatically. And that submission scripts, there's the output from the queuing system, but we are not going to look at those. So now this was all copied. I see it copies a little bit too much. I see that it has all written the references, if I'm not wrong. That was not the idea, but let's see. So here, yeah, as you have seen already in the previous days, you will have some ready prepared files. So this is a GNU file, and this file directly plots. It uses the values which were gained on the cluster, and it plots them here with the GNU plot. So you can just take GNU plot. There are lots of these options. We are not going to go through them, but this will show you this 2-dimensional potential surface. So you see, you have this A value of the lattice constant. This was the lateral lattice constant in the hexagonal cell. And on the other axis, you have the C. And now in this contour and contour with the lines and the colors, you see the representation. And you see that the lowest energy, I mean, that has been normalized to 0. So that's the minimum. So that's the most blue point. So it's somewhere here, 2.61 for A and 5.27 maybe for the C. So this would be very roughly with the eye looking at this output and concluding the optimal lattice constants A and C from this calculation. So this is what you get. This you can have a look then with the GNU plot. In the meantime, we can execute. Actually, I wrote it already. I mean, this is all in the files, the README files also. If you want, then, well, now it's very crowded. This, but you have the README. Well, now it's somewhere in between. There's the README MD, so you can have the exact commands there. So we can launch the remote MPI run for this other job also. So it was remote MPI run, then the executable dash in and the input file, and you don't redirect the output. Otherwise, it's like you will be running interactively on a cluster. So the remote is just this complicated script which launches the job and does all these steps for you. So we try to launch that, and let's see if I'm lucky. So again, it says the job was launched on the remote cluster using 20 cores. So 20 has been chosen actually because I think this is the number of cores per node on that. Well, on let's say on all the clusters, it's a kind of optimal value. And we can check the status of the job. So now it's running since 24 seconds. And now while it's running, you can, for example, look at the potential surface and so on. Does anyone have problems so far? Everyone is able to run MPI run remotely, PWTK remotely. Everyone is happy. Everyone gave up.
The only thing I think that we should we could now close the streaming session if you agree. So I would I mean I would thank, I don't know, look if there are any left questions. Otherwise, I mean, we'll thank the participation on streaming. I think we can close the streaming and the registration as well, and we can stay available for the ones that needs help in here.
Yeah. So then the rest of the exercises you will see.
Hello.
Yeah, Ivan, isn't it half an hour more for the streaming?
Yes, but we stay here, but we close the registration and the streaming. I mean, we don't need to register ourselves that we chat one another.
Okay, but there are still examples.
We leave the Zoom open, but I don't know. I mean, what do you think?
But I think that Ari has still something,
there are still some exercises to explain. So
okay, perfect. No, sorry. I thought we were just left to the exercises.
No. Now I thought we take some time because.
Excuse me. Please go ahead.
No problem. No, I mean we are going a bit slower than initially we had planned, but I think it's good, like you said, that we try to slow down. So we hope that everyone has managed to run remotely. So
someone has problem with remote access. Okay. Maybe one can check.
Is that on
Zoom?
On Zoom.
Amal Aldara.
Yeah, I told to Amal to join the breakout room. If he can join the Mondal breakout room, I will be able to.
Okay. Yeah.
To help him.
Yeah. So you can also invite this person.
Yes.
Is it Amal who has problem? If anyone has problem, please report now. I mean, you can also write quickly on the Zoom or Slack chat, and then we can use these checkout rooms. So someone will invite you, or you get an invitation that you can join there if you have any trouble. So in the meantime, well, I mean, later, if you now in the breakout room, well, you don't hear me anymore if you're in the breakout room. But if you go to the breakout room, you of course have these slides, and you can ask us later how it continues. But I think it's all clear. You continue, and if you have any questions afterwards, then we will have the Slack also later during this week. If you have questions related to this day, we are there to help you. Okay, so in the meantime, the job had finished. I think it took something like 2 minutes. So this VC relax. So I will quickly explain the aspects. So now there's much less output because there was only one job. There was no loops. Sorry, now I made a mistake. Using the wrong keyboard shortcuts. I hope we are back to my. Well, now I see the resolution is again much higher. I try to go to lower resolution, so it's bigger fonts and so on. It's this one. Sorry, this is my mistake. Well, sorry, it's still too high.
Ari, you can leave default, but then you set up the resolution in the virtual box.
Yeah. No, because I managed to do it this morning. Just now, for some reason, it always wants to go back to the high resolution.
No, but you are trying now to set the resolution within the virtual machine.
Yeah, I did it this morning, and I think it worked fine. But sorry, I tried once again. Because then, yeah, I saw that it was okay for my screen. Okay, yeah, sorry, I took the wrong one. No, it again adapts to high resolution. Sorry, just I don't know why it goes back to this. Because I do the resizing of the screen and it goes back. It keeps on. So I try not to do it. Well, I try to do it now. Sorry for that. Yeah, I try to stay at this size.
Ari,
yeah.
You are now trying to set the resolution within the virtual machine.
Yeah, I know.
Better if you do it from the virtual box.
Yeah, I don't know if it's a good time now, but display. I think I try to survive. So, or we'll do it later when the people might be waiting for some. So I hope now. I see the width is not okay, but I hope you can still read my font at this moment. So I did the copy, and I think now it's gone. I just check. Well, so now we visualize these outputs that we got from the remote cluster. So this was the VC relax calculation, and this is the output. So now we don't reduce dimensionality because this is actually a really three-dimensional system. I only show the final geometry. It's not very interesting because it actually only changes the lattice constants. So this is the HCP crystal. Not very interesting as such. And as I mentioned, the symmetry is so high that there are no internal degrees of freedom. So let's have a look on the, just reading a little bit the output file. And again, how many steps you need, that depends on the initial geometry, how far it's from the final value, the final lattice constant and the geometry. So I just mentioned here at the beginning of the outputs, they are the crystal axis in Cartesian coordinates in units of ALAT, because this is what is interesting later in the output. So otherwise the output is the same, it just repeats those. Then it does the first self-consistent loop. It shows the eigenvalues at the different k points. So now we are not only at the gamma points, we had quite many, sorry. Then we had the forces, and no surprise, the symmetry is so high that all the forces are zero. So there's no internal degree of freedom in the coordinates to optimize. But the lattice constants, they need to be optimized. And now we see the value of the stress tensor. So you can let it print also if you don't do VC relax. There's a value input variable in the control section. You can check it up in the documentation. Again, in the browser, you can click on the input variable, so the description of the inputs for BW.x. But here it's automatically printed because we are doing the VC relax calculation. And it shows the value of the stress tensor. Actually, it shows here it already shows the isotropic one, so that's the trace, and that already gives you an idea. If it's a very large one, like here, it's this value is in kilobar. So here, the stress tensor on the left, sorry, I cannot show, but these values, well, by symmetry, most of them, the non-diagonal ones, they are zero, but the diagonal ones, they are in Rydberg by Bohr to the cube. So this is, you can imagine, this is the energy or change in energy when you change the volume. So that's why it's Bohr cubed. or the atomic unit for the length, cube. On the right, you have the same values in kilobars. If you want to think in other units of pressure, you can do the conversion. So, but here is the value, like I said, this is the average value, the trace, divided by 3 of the diagonal. And this gives an idea. If this is a large one, you probably have a large stress still, and the calculation will continue. Now, again, we do BFGS on the coordinates. There's nothing to optimize. And we do, is it also BFGS by default on the lattice? So it looks almost the same. There's just a pressure tensor. But what does change then? The code does not only show the new coordinates, it also shows the cell parameters. And I mentioned initially it shows the initial values in the units of ALAT. Now it does the same in units of ALAT, which is this one. And the first one, I think in all cases, it starts from 1. It's 1.0000, no matter which system, because these are in units of ALAT, and ALAT is always this first. So you had to multiply all these values by the ALAT to get the actual lattice constants. And again, ALAT here, it's in atomic Bohr units. It's not in Ångström, no matter what you gave in the input. Now we see that the value here, it has changed a little bit from 1. So it's about 3% larger. So the lattice laterally has expanded about 3.4%. I don't remember the value in the third direction, but it also has changed. Okay, so this was after the first step. And we saw the pressure is about 185 or 186 kilobar. Oops. And now I search for this. So after the second step, now we had 60 kilobar. So that's again the average of the diagonal. So it has reduced. And again, we have new values for the lattice vectors here and the new atomic positions. The new atomic positions, they are very boring because they are optimized in the crystal lattice coordinates, which was given in the input. So they are relative with the lattice constant. This is what we want here, because the coordinates will be always this. Again, the forces were always 0 because of the symmetry, so these won't change. If you would want to have the coordinates in angstroms, for example, in Ångström, then you would have to multiply these with the lattice vectors, and the lattice vectors have been changed during the relaxation. Okay, we go to the next steps. Again, the value reduces, now it goes negative, so you might have gone a bit to the other side, but eventually we hope now it's the next steps, it's reducing again. Now it's small, and this is now the final calculation, the last step. And so this is now what it gives as the final. Oh, sorry, I went one too far. This is already this extra relaxation that Pietro mentioned this morning. So we had to go to the second last one. Okay, here we are. Sorry for that. So this is the last iteration during the relaxation. And now you see that the value is, well, it's like negative, it doesn't matter, but it's very close to 0. And this is considered converged. So now we have converged both the coordinates, or the forces on the atoms, and the lattice vectors. Well, on the forces in this example, it was very boring because it was only, they were always 0 because of the symmetry. But otherwise, the calculation has converged also with respect to the stress tensor. And now we have, again, this final section in the output. So here you see the lattice vector. In the hexagon case, laterally, it has expanded by 3.35%. And this is probably due to the GGA. Well, could be also if the cutoff number of K points is not converged, but those you can always increase. But at the end, you will see that you have some difference with respect to experimental values. And well, main part of that is to the exchange correlation. It could be that the experiments stay also at finite temperature. If you are lucky, you find the values which have been extrapolated to 0K. And they are the nuclear quantum effects, 0-point effects, and so on. But I would say normally you will have 1-2%, two large lattice vectors, lattice constants, if you use the GGA in normal materials, not the Van der Waals cases and so on. So these are the final values, and this is the final result from the calculation. And now this one we could use. So the ALAT was 4.80, and the lateral, I only take the lateral value. So now use a calculator. So we had 4.80, and then we have times 1.033 something. So this is the final lattice constants from the calculation. And then if you want to get to angstrom, this would be more or less 2.62. So this would be the lateral lattice constant, the final value in angstrom. And if you remember, the manual way, I roughly said from the screen 2.61. So if one would do it more carefully with more time, you would see that these should be pretty close to each other. And the better you are converged with the cutoff and the K points, the closer you are with it by these two ways. The normally one is, I must admit, usually one is lazy, one uses one method or the other. There are also other ways to do it, but you should at the end get the same result. So if you do it the manual way, the two-dimensional, here we have two-dimensional scanning of the total energy, or if you do the VC relax. Then if you will have more complicated examples where you have more than two lattice vectors, then usually you have even different angles. Now we had this 120 degrees in the hexagonal cell, but then 90 degrees, so the direct angle between the lateral and the vertical. So there were only the A and C. But if you have a more complicated ones, I must admit that most people, me included, would use the VC relax way. But please be careful. There's this issue with the convergence with the cutoff energy and this finite base set that was explained by Pietro. So there are tricks and, well, tricks or ways how to try to minimize the error due to this. But we don't have time to go into this today. If you have any problems, any questions? So those of you, if you want, at this point, you can go to the next example. This is just a small modification of the previous one. So this again, you would probably want to launch this remotely. So you see, this is a direct input file for the pw.x. So you would use remote MPI run if you want to execute this. This will take again some minutes to launch. And the difference here is that now all the forces with respect to the coordinates, they are not zero by symmetry. In this case, so this is a crystal of urea. So it's actually a molecular crystal. So urea is a small molecule, and it has its bond length and so on. So these all depend on also on the interaction between the molecules. So now we would, in this example, you will see that you will not only relax the lattice vectors and the atomic coordinates, the forces are zero on the atomic coordinates. This is not the case here. So you will be relaxing both at the same time in this example. But I suggest that we carry on further. We are running soon out of time. And I will now quickly explain the last exercises, and then you will independently continue those. Independently, we will have the tutors, and me, Tone, will be around, not only until, well, it should end in 15 minutes anyway, but we'll be available sometime later. If you have any questions, of course, we are available on Slack. So now I will use the rest of my time, I think 15 minutes, trying to explain what is left in the exercises. But if you don't want to listen to me, if you are confident, you can do it without some explanations. You can carry those. Otherwise, it's time that it's called you sit on your hands and don't use the keyboard. That's a way to say that you don't try to execute all the commands at the same time and trying to listen. But if you try to listen, I will try to quickly explain the rest of the exercises. And then again, we have the chats and we had the breakout rooms if you have any problems or any questions. So this is the example 2. Example 3 is an example on the notch elastic band. This was what Tone explained this morning. And this is the first one is very simple example. I will not go into details. It's very funny that even if you have only a few hydrogen atoms, this could be very difficult for the DFT to be converged. That's because of some issues. We don't have time to go. It sounds like a very simple system, but also if you charge this, it will be horrible to treat with any of the exchange correlation functionals. But now we just believe that everything works. So we will use DFT to get the forces. Everything is fine. In the first case, example 1a of the NEB, we start the calculation using no intermediate image. I mean, Tony explained you can use these intermediate images. And here we just start, and I will show you already some slides later, you will see. So we have the initial state, the first image, which is that the two hydrogens are close to each other, and then there's the third hydrogen a bit further away. The last one is just we have exchanged the central hydrogen, so it's very easy to imagine. They are all on a line in this case. Actually, it's there's one could say only it's a one-dimensional system, or if you think it's two distances, but if you consider the difference of the two distances, then you will have only one dimensional potential surface. But anyway, this is the first image. This is the final one. The difference is that you have shifted the central hydrogen from one side to the other one. And now we want to calculate the energy barrier for this reaction. And the default method, if you don't use these intermediate images, it's just one does linear interpolation. So this would be the central image. Depends on how many images you will be using. You will have some intermediate images between the first image and the central one, and then the last image and the central one. So basically, you just interpolate between the first and the last one, and this image in the middle is just a consequence of this linear interpolation. So the more points you have, of course, little by little, the hydrogen is shifted, because again, linear interpolation is done numerically. There's no DFT, nothing. It just takes the initial coordinates, the last coordinates, and this is linear interpolation. And Tone mentioned, please don't swap the atoms or anything, otherwise you will get horrible, well, I won't call it anymore chemistry, but some very difficult geometry. So here, because the first image, final or last image, you have the same coordinates for the first and the last hydrogens, they will remain the same in this linear interpolation. So only the central hydrogen is shifted. So this is the first example, example 1a. Again, on the examples, the inputs, and so on, they are given. And here we use 7 images. And what you will get is then, once you run the examples and GNU plot, you will get a plot like this, where you get the reaction barrier. So you go from the initial state 0 to the final state. It's just the reaction coordinate is given in arbitrary units. Actually, it's a scaled units. So you see it goes from 0 to 1, and it's symmetric. And we saw it already. This, if you have the H2 first on the left, on the right, it's the same. So that's also why the potential in the surface will look symmetric. The second one is a kind of numerical exercise. This is now using the intermediate image. If you use this chemical intuition, we can imagine, okay, and the real reactions, the last hydrogens, they don't want to stay where they are all the time. And this is the initial configuration that you will get using just this linear interpolation. But probably in the intermediate one, you will have something like, well, a symmetric molecule when the three hydrogens are closer to each other. So again, the initial, or the first hydrogen, it has gone a bit further with the central hydrogen, and the hydrogen initial on the right has come a bit closer to form this kind of image. And so this you can insert using this intermediate image, and then you give the system or the computer code kind of more information than just the linear interpolation. And sometimes the linear interpolation doesn't even work. You might have a reaction. For example, you have an atom which goes from my one hand to the other one, but there's an atom in the middle, and you want to see the diffusion above it. Now, if you take the linear interpolation, you will kind of shoot. You have a direct line in the linear interpolation, and the two atoms would come very, very close. So in this case, the linear interpolation would not work, and you have to go to something like intermediate image. So it depends again on your system. You might be forced to use this. In this case, you can calculate also using this linear interpolation. And the idea here is to look at the difference. Well, you should get the same potential in the surface at the end. Sorry, here independently, but it says that the computation it's more efficient to give this intermediate image. So you will check how many steps you needed to get to the converged potential in the surface. This is the idea of the first exercise. Then the second one is again a net calculation, and again here we will use the intermediate image. The physical system is H2 dissociation on a metallic surface, the so-called 100 direction of the aluminium surface. Aluminium, you have seen the example before. In the earlier days, it's a FCC metal, and then we cut the surface along the 100 direction. And now we want to see what is the energy barrier for the H2 dissociation. Is there a barrier, and how high is it? And what is the initial state? Well, that's H2 in the vacuum. And then it would slowly approach. And what would happen chemically? Well, you will see also in the movie or in the visualization when you visualize the structure in the intermediates. And the final state, dissociation, is that there are two hydrogens which are on the surface. So depending on the reaction, they might dissociate and remain quite close. It could be that initially they already dissociate and go further away. What usually happens is that they will stay quite close, but then also due to the diffusion, then the other atom will diffuse further away from the initial one. This is now quite simple. You will see it's only two layers. Also laterally, the cell is too small. This was just to keep the calculation reasonably fast. So again, this would not be sufficient for a real scientific project, but you will see the idea. You will get the idea from this example. And then there's the scripts, PWDK, and then the commands, how to run this example also remotely. And then you will plot this potential surface again, and you can visualize this intermediate ones. So you will see what happens chemically. And then later, if you want to continue, we can discuss also how it looks like. And if you have questions, what happens? Why does it look like this? We can do this later. But idea is now I just will give you a quick glimpse what you are going to do, and then you execute them. And then if you have questions later, you will have us probably explaining it. Then there's actually now we have a short tutorial on PWTK. Thanks a lot to Tone for contributing this wonderful software. And we will use it further also the more complicated quantities. You have done already this convergence test and so on using this very nice way of creating loops inside PWTK scripts. We will use that also for other kind of analysis, which will be again more complicated without the PWTK. And the first example is just, well, equation of state. We will be looking how to calculate the equation of state of material. The second one will be the adsorption of oxygen on aluminium 111. So this is very similar to the previous one. Sorry. So this was the one 0, 0 direction of the surface, the 1, 1, 1 would be a different orientation of the surface. And we will be looking the potential energy surface of oxygen at different places of this oxygen laterally on the aluminium 111 surface. And then the third one, this is more elaborate, and we have already written in the slides. This is left as a homework. If you want, you can continue. I think the reservation will continue, so you can continue during this this session. Also, if you have questions, there will be actually a very nice chemistry going on. This CO adsorption on metal surface is chemically very interesting. It has been discussed a lot, and that there are lots of works on this. So it's very intuitive also chemically. And for those of you who want to look it up, so it's the so-called Bleiholder model, which was initially proposed to explain the chemistry of the CO adsorption on surfaces. If you want to read something more boring, you can read my thesis. This was one of the topics I was studying during my PhD thesis, adsorption of CO on, I think it was a ruthenium 0001 surface. So that's why also I know this, but actually the example doesn't come from me. It comes from the previous edition of school. So these are the three examples here in the final section. So there's some explanation of PWDK, but then there will be the explanation how you would run this calculation of the bulk lattice constant of rhodium in this case, because you saw the third example is rhodium surface, rhodium 100. And this is now we will be fitting the lattice constant, and you will get while using different analytical forms of the potential energy as a function of the volume. So this is what you will get in the outputs. Then the second example was this oxygen and aluminium. Again, here we are going to do a loop using BWDK where this oxygen goes along the surface. And here, maybe I mentioned here, it came already during the previous example. If it was not mentioned already, how you can fix atomic coordinates during the relaxation. And also, I think if it was not mentioned, you can fix during the optimization of the lattice vectors. You can, for example, fix one of the lattice vectors, two of the lattice vectors. There are different ways. And you can imagine if you want to optimize, for example, the lattice vector of graphene. So you know it's only a one sheet. So not graphite, but graphene, one sheet. And then we had this vacuum between the layers. And there, even if you would take a large amount of vacuum in the vertical direction to separate the sheets, there is always some residual pressure calculated by PW.x. And then it would start to modify the amount of vacuum. I don't remember if it would try to, well, bring the layers together. So there it's actually preferable to keep the layers apart. And there are options in the relaxation. It's so-called the cell do-free option. You can look that up. That's in the cell section in the input for PW.x. I just mentioned it here because I think it didn't come before. And the same here, I just show, here we insert the oxygen atom. And well, I show this. So this is then what you will get actually as a output. So you will get the potential energy of the oxygen when it's laterally at different positions along this aluminium 111 surface. This is what you will get as an output. But we want to have the height of the oxygen relaxed during this calculation. And how we can achieve this is that we fix laterally the coordinates, and these are, it's not the input for PWX, this is BWTK, but it's the same thing. So you give the three coordinates, no matter in which units, and then you can put three values, which are either 0 or 1. And 0 means you fix this coordinate. 1 means you relax this coordinate. So these are three integers. You can leave them out. This means relax all those. If you specify, I think if you specify one of them, you have to specify all three of them. And they can be only 1 or 0 or 1. Again, 0 means it's fixed, and 1 means that this coordinate is relaxed. Here we wanted to keep the oxygen laterally fixed for each of these position in the 2D scan of the potential surface, but we want to relax its height. I think the substrate gets fixed just to keep calculations fast. And this way, well, we come to this. So at each lateral position, we have vertically relaxed. So we have optimized the height, and that's why we have only 2 independent variables. So that's 2 lateral coordinates of the oxygen. Again, these are the commands that you can execute. It's better to run remotely because this takes quite a while, because you have this double loop again, and now you do some relaxation and some metallic system and so on. So this was the second. And then the third one was this CO adsorption on rhodium 100. And this, again, it's left as a home exercise. If you have time, if you are interested, you can do it at the end of this session. We are there to help you if you want. And you will see that you will get some other properties. We can get the density differences, so-called. So this is to analyze how the how the density, electron density changes when you adsorb, in this case, the CO on the surface. This is then a different quantity. This is kind of energy result change in the electron density. So from this is not the difference, but you could calculate also the difference in this way. So we take energy range and we calculate all the orbitals that contribute to the density in that energy range, because we have all the eigenvalues and all the K points. So this is another example that you will be calculating. And then you will have the projected density of states, which was calculated already before. And then we have some additional, more complicated way of doing the projection. Here we project the wave functions in our system. So in this case, the adsorbed CO on the metal to the orbitals of the free molecule. And this is again, can be used to analyze how the chemistry changes upon this adsorption. So this is another quantity which is nowadays implemented, and it's, well, I would say relatively easy to use. So you will see in the inputs if you come that far. If you don't manage to do it today, no worries, you can do that later. I mean, either later during this week or then later in your home computing cluster or on another machine. But this is again for the analysis. And then this is, yeah, the molecular orbitals of the carbon monoxide. So this is the adsorbate. And so the projection here, these are the different orbitals. So for each orbital, you would get its own graph, and they all depend on the energy. So for each orbital V, you have this curve as a function of energy. If you have any questions on these quantities, again, this is meant as a kind of advanced properties. And this also shows the advanced methods that you can use with BWTK. So now I'm gone through all the exercises. Now it's time for you to start playing. If you haven't done it yet, you can start playing. Again, we will be there to guide you, to help you. If you have any questions, comments, I don't know, we take now. Soon we will stop the streaming. So this is your last chance. If you have any questions at this point, those who are registered, we will remain there on the Zoom and Slack. But if anyone is there,
okay. So Ari, thank you very much for this wonderful presentation with all these details for practical exercise. So I think we can close the session now, and we can all meet in Slacks to follow the exercise, or for any problem or questions and so on. All the tutors will be there, and also, I guess, Ari. For those who are streaming, maybe they can ask some questions. There will be also tutor there. So thank you very much, and see you on Slack. Thank you.
Thank you.
Thank you very much. Goodbye.
Bye again. Bye.
Bye-bye.
Thank you, Tom. Thank you again.
Thank you very much. Thank you. Bye. See you.
So we will lose the Zoom, right?
I don't know.
I mean,
Ivan.
No. We leave the Zoom on.
Yeah,
We leave
yeah,
the Zoom on.
that's what I thought. Yeah.
We leave the Zoom